There is a place in the universe where nothing exists. Not darkness in the way you imagine it. Not the darkness of a room with the lights off. Not the darkness behind closed eyes. Something far more absolute. A region so vast, so thoroughly emptied of stars, gas, dust, and signal, that if you were somehow placed at its center, you would look in every direction and find nothing. No light, no warmth, no reference point, no edge visible from where you stand. Just an ocean of space so deep and so silent that the concept of direction would begin to lose meaning. You would not know which way was out. You would not know how far the emptiness extended. You would only know that it extended in every direction, further than you could measure with your eyes or your instruments or your fear. The window is still open. For now, if you're one of the minds that doesn't look away, subscribe to Beyond the Universe, before the silence gets here. This is not a thought experiment. This place exists, and what makes it truly unsettling is not its emptiness. What makes it unsettling is the growing suspicion among those who study it that the emptiness is not passive, that it is not simply the absence of something, that it may in fact be doing something, shaping the universe around it, pulling and redirecting the flow of matter across distances that dwarf entire galaxy clusters, operating according to rules we have only recently begun to suspect and not yet come close to understanding. For now, the window is still open. If you're one of the minds that doesn't look away, subscribe to Beyond the Universe before the silence gets here. Begin with what you know, or what you think you know. Look up on a clear night, far from city lights, and the sky appears full. Thousands of stars scattered across the dome of the atmosphere, the faint smear of the Milky Way arching overhead, the occasional soft glow of a planet. It looks populated. It looks like a place where things are happening. And in a narrow local sense, it is. But that impression, that sense of a sky full of light and presence, is one of the most misleading perceptions the human mind has ever constructed about the nature of reality. The stars you see with your naked eye are, in cosmic terms, your immediate neighbors. The closest one beyond our own sun, Proxima Centauri, sits roughly 4 light-years away. That means the light entering your eye right now left that star 4 years ago, traveling at the fastest speed anything in the universe can travel, and it still took 4 years to reach you. 4 years of uninterrupted travel through vacuum, through nothing, to cross the gap between 2 adjacent stars in the same small corner of the same galaxy, and that is the closest one. Now pull back. Imagine rising above the Earth, above the solar system, above the plane of the Milky Way, until our entire galaxy, a structure containing somewhere between 200 billion and 400 billion stars, appears as a single flat disk of faint light below you. From this distance, the galaxy looks dense. It looks like a solid thing, but it is not. The average distance between stars inside the Milky Way is roughly 5 light-years. 5 years of light-speed travel on average separates each star from its nearest neighbor. The galaxy is not a crowd. It is a scattering, a thin dusting of points across an enormous volume of space that is, by any honest measurement, almost entirely empty, and the Milky Way is just one galaxy. Pull back further. Watch it shrink. Watch it become a point of light among other points of light. The local group, a collection of roughly 80 galaxies bound together by gravity, spread across a region of space approximately 10 million light-years across. 10 million light-years. The number is so large it resists comprehension, but try to hold it, try to feel the weight of it, because even within this gravitationally bound family of galaxies, the space between them is vast, cold, and almost entirely devoid of matter. Pull back further still. The local group is itself just one small cluster within a larger structure called the Virgo supercluster, which contains hundreds of galaxy groups and clusters spread across a region roughly 110 million light-years in diameter. And the Virgo supercluster is itself just one lobe of an even larger structure, a cosmic filament, a thread of matter stretching across hundreds of millions of light-years, part of a web so enormous that the entire observable universe is required to contain it. At this scale, something becomes visible that is invisible from the ground. The universe is not uniform. Matter is not spread evenly across space like paint on a wall. It is gathered, concentrated, threaded into long, thin structures, filaments and sheets and nodes, and between those structures, there is almost nothing. The universe, seen from far enough away, looks less like a solid object and more like a foam, or perhaps more accurately, like the skeleton of something that was never quite built, a framework of matter surrounding enormous hollow chambers, regions of space where the density of galaxies drops to nearly zero, where the cosmic web simply stops, where the architecture of the universe gives way to something that has no architecture at all. These hollow chambers are called voids, and they are not rare. They are not anomalies or exceptions. They are, in terms of volume, the dominant feature of the universe. If you were to take the entire observable universe and divide it into regions of matter and regions of emptiness, the emptiness would win by an overwhelming margin. The filaments and walls and clusters where galaxies live occupy only a small fraction of the total volume. The rest, the vast majority of the space the universe contains, is void. This is the first thing that should disturb you. Not the existence of empty space, which is expected, but the proportion. The universe is not mostly stars and galaxies with some empty space between them. The universe is mostly empty space, with thin threads of matter clinging to the boundaries of enormous hollow regions. The matter, all the stars, all the planets, all the gas clouds, all the galaxies, is the minority. The emptiness is the majority, and the emptiness has shape. Consider what it means for something to have shape. Shape implies structure. Structure implies that something organized it. And when you look at the large-scale distribution of matter in the universe, when you map the positions of millions of galaxies across billions of light years, what you see is not random. The voids are not randomly placed. The filaments are not randomly oriented. There is a pattern, a vast, three-dimensional pattern of interconnected structures and hollow spaces that cosmologists call the cosmic web. And it is one of the most extraordinary things the human species has ever discovered about the nature of the universe it inhabits. The cosmic web did not appear by accident. It grew. In the earliest moments after the universe began, matter was distributed almost uniformly, but not perfectly uniformly. There were tiny fluctuations, microscopic variations in density, regions where matter was infinitesimally more concentrated than the surrounding average. Gravity, patient and relentless, began to work on those fluctuations. Over hundreds of millions of years, the denser regions attracted more matter. The less dense regions lost matter to their neighbors. The fluctuations grew. The dense regions became filaments and walls. The underdense regions became voids. And the voids grew too, not by accumulating matter but by losing it, as gravity pulled everything toward the surrounding structure, leaving the interior of the void progressively more empty with each passing billion years. The voids, in other words, are not static. They are expanding, not in the way the universe expands, not because space itself is stretching inside them, though that is also happening, but because the matter that once occupied their interiors has been gravitationally evacuated, drawn outward toward the filaments and walls that define their boundaries. A void is not simply a region where nothing formed. It is a region that was actively emptied, and the process is still ongoing. Stand at the edge of one of these voids, not literally but imaginatively in the way that cosmological thinking sometimes requires, and look inward. The boundary of a void is not a sharp wall, it is a gradient, a slow thinning of galaxies, a progressive dimming of the cosmic web, until the filaments fade and the last faint galaxies disappear and there is nothing ahead of you but open space. The transition from structure to emptiness is gradual, like walking into a fog that thickens until you can no longer see your hand in front of your face, except that here the fog is lifting rather than thickening, and what it reveals is not clarity, but absence. The typical void in the observable universe spans somewhere between 30 and 300 million light-years across. These are not small features. A void of 100 million light-years in diameter contains a volume of space so enormous that our entire local group of galaxies, 80 galaxies, 10 million light-years across, could fit inside it thousands of times over. And yet, inside that volume there are almost no galaxies, almost no stars, almost no planets, almost no atoms arranged into anything recognizable. Just space, just the slow, cold expansion of a region that gravity has abandoned. But it gets worse, because among the voids there are supervoids, regions that make the typical void look like a puddle beside an ocean. The most famous of these, or perhaps the most infamous, is a structure sometimes called the Boötes void, located in the direction of the constellation Boötes, roughly 700 million light-years from Earth. When astronomers first began mapping this region in the 1980s, they expected to find the usual distribution of galaxies, clusters, filaments, the familiar texture of the cosmic web. What they found instead was almost nothing, a roughly spherical region of space approximately 330 million light-years in diameter, containing only a handful of galaxies where there should have been thousands, 330 million light-years. Pause on that. If you placed our Milky Way galaxy at one edge of the Boötes void and tried to cross it at the speed of light, the journey would take 330 million years, not 330 million miles, not 330 million kilometers, 330 million years of travel at the maximum speed the laws of physics permit, and you would still be inside the void. You would still be surrounded by nothing. The crossing would take longer than the entire history of complex animal life on Earth, and this leads to something more disturbing. The Bode's void is not unique. It is simply one of the better studied examples of a class of structures that appear throughout the observable universe. There are other supervoids, some potentially even larger, some less well-defined, some still being mapped as our instruments improve. The universe is riddled with them. These enormous hollow chambers are not exceptions to the rule of cosmic structure. They are part of the rule. They are as fundamental to the architecture of the universe as the filaments and walls that surround them. What does it mean that the universe contains structures this large? It means that the universe, at its largest scales, is organized in a way that produces not just emptiness, but profound, structured emptiness. Emptiness with geometry. Emptiness that has boundaries and gradients and a relationship to the matter around it. Emptiness that is, in a very real sense, a feature rather than a flaw. And if emptiness is a feature, then the question becomes, a feature of what? What kind of universe produces these structures? What kind of physics generates voids of this scale? And what, if anything, lives inside them? The answer to that last question is almost nothing, but almost is doing a great deal of work in that sentence. Because even inside the deepest voids, even in the most thoroughly evacuated regions of the cosmic web, there is not true nothingness. There is something, and the nature of that something is one of the most philosophically challenging aspects of modern cosmology. Empty space is not nothing. This is not a poetic statement. It is a physical one. The vacuum of space, the space between galaxies, the space inside voids, the space between the atoms in your body, is not a passive absence. It is a medium. It has properties. It has energy. It fluctuates. At the quantum level, the vacuum is a seething, restless environment in which particles and antiparticles constantly flicker into existence and annihilate each other in intervals so brief they cannot be directly observed, only inferred. The vacuum is not still. It is never still. It hums with an energy that has no source we can point to, no origin we can trace, no off switch we can find. This vacuum energy, sometimes called zero-point energy, sometimes folded into the broader concept of dark energy, is one of the most mysterious quantities in all of physics. It is real, its effects are measurable, and yet its nature is almost entirely unknown. We know it exists because the universe is behaving in a way that requires it to exist. We know it has consequences because those consequences are visible in the large-scale structure of the cosmos. But we do not know what it is. We do not know where it comes from. We do not know why it has the value it has. And the value it has is, by any theoretical expectation, absurdly, inexplicably small, which is itself one of the deepest unsolved problems in physics. But set that aside for a moment. Set aside the quantum vacuum and its restless energy. Focus instead on the simpler, more immediate strangeness of what empty space actually is. When you look at the void between galaxies, when you imagine yourself floating in the interior of the Bode's void, surrounded by 300 million light-years of near-nothingness in every direction, you are not looking at nothing. You are looking at space itself. And space itself is something. It has geometry. It can curve. It can stretch. It can carry gravitational waves, ripples in its own fabric, generated by colliding black holes or merging neutron stars, propagating outward at the speed of light through the very medium of space. Space is not a container that holds the universe. Space is part of the universe, and the emptiest regions of space are not outside the universe. They are inside it, shaped by it, participating in it. This distinction between empty space and true nothingness is not merely philosophical. It has consequences. Because if empty space is something, then the voids are not simply regions where the universe is absent. They are regions where the universe is present in a different form, a form that is harder to see, harder to measure, harder to understand, a form that may be doing things we have only recently begun to suspect. Here is one of those things. The voids are not gravitationally neutral. Even though they contain almost no matter, they are not isolated from the gravitational influence of the matter around them. The filaments and walls that define the boundaries of a void exert gravitational pull on everything inside it, including the sparse galaxies that happen to exist near the void's interior. Those galaxies are being pulled outward, toward the surrounding structure, which is part of why the voids are emptying over time. But the void itself also has a gravitational signature. Because it contains less matter than the average density of the universe, it behaves in a sense like a region of negative gravitational influence, a place where the gravitational pull is weaker than average, which means that matter flowing through the universe tends to be deflected away from voids and toward the denser regions of the cosmic web. The voids, in other words, are not just passive holes in the cosmic web. They are active participants in the flow of matter across the universe. They push, not with a force exactly, but with the absence of a pull. They are the negative space that defines the positive structure, and without them, the cosmic web would not have the shape it has. The filaments would not be where they are. The galaxy clusters would not have formed where they formed. The voids are not the leftovers of cosmic structure. They are part of its cause. And this leads to a question that sits at the edge of what we currently understand. If the voids are shaping the distribution of matter, if they are active participants in the architecture of the universe, then what shaped the voids? The answer, as far as we can tell, begins with those tiny fluctuations in the early universe, those microscopic variations in density that gravity then amplified over billions of years. But the amplification required something to work with. It required that the early universe was not perfectly uniform. And the reason it was not perfectly uniform, the reason those initial fluctuations existed at all, takes us into territory that is still being mapped, still being argued over, still being revised. One possibility, and it is a possibility that most cosmologists currently find compelling, though the evidence does not yet prove it beyond all doubt, is that the universe underwent a period of extraordinarily rapid expansion in its earliest moments. A period called inflation, during which the universe expanded by an enormous factor in an almost incomprehensibly brief interval of time. During this expansion, quantum fluctuations, the same kind of restless, flickering variations that characterize the quantum vacuum, were stretched to cosmic scales. What began as microscopic variations in the quantum fabric of space became the seeds of the large-scale structure we see today. The filaments, the walls, the voids, the supervoids, all of it, according to this picture, traces its origin to quantum noise stretched across the sky by a process that lasted less than a fraction of a second and that we cannot directly observe. If this is true, then the cosmic web, including its vast empty voids, is a kind of fossil, a record, written in the distribution of matter across billions of light years, of events that occurred in the first unimaginably brief moments of the universe's existence. The emptiness you see when you look at the Bode's void is not random. It is the echo of a quantum fluctuation that happened before the first atom existed, before the first photon traveled freely through space, before time itself had accumulated enough of itself to be measured in any unit a human mind can grasp. That is the scale of what we are dealing with. That is the depth of the connection between the smallest and the largest things in the universe. And it is only the beginning of what the emptiness is trying to tell us, because the voids are not just fossils of the early universe. They are also windows into something that is happening right now, something that is accelerating, something that is changing the future of every galaxy, every star, every atom in the observable universe, something that lives not in the matter of the cosmos but in the space between it, something we have named but not understood, something that may be the most consequential force in the history of the universe, and that we discovered, almost by accident, less than 30 years ago. The universe is not just expanding. It is expanding faster than it should be, and the reason it is doing so, the thing driving that acceleration, appears to come from the emptiness itself, from the void, from the space between things, from the very nothingness that we spent so long assuming was passive and inert and irrelevant. The emptiness, it turns out, is not empty of consequence. It may be the most consequential thing in the universe, and what it is doing to the future of everything that exists is something we will need to follow much further into the dark to fully understand. But before we go there, before we descend into the deeper implications of what the emptiness is doing and where it is taking everything, it is worth pausing here, at the edge of the first revelation, and simply sitting with the scale of what has already been described. Because the human mind was not built for this. It was built for savannas and seasons, and the distances between one place and another that a body can walk. It was not built to hold 300 million light years in a single thought. It was not built to feel the weight of a void that could swallow thousands of galaxy groups without noticing. And yet here we are, using instruments and mathematics and the accumulated effort of generations of human curiosity, staring into a darkness so vast and so structured that it forces a question that has no comfortable answer. What are we in relation to this? Not philosophically, not in the sense of meaning or purpose, which is a different kind of question, but physically, spatially. What is the relationship between a human being standing on a planet, orbiting a star, inside a galaxy group, inside a supercluster, inside a filament of the cosmic web, surrounded by voids that dwarf everything we have ever named or measured. What is the relationship between that human being and the structure of the universe they inhabit? The answer, stated plainly, is that we are an almost infinitely small feature of an almost infinitely large structure, most of which is empty, most of which we cannot reach, and most of which does not know we exist. That is not a comfortable thought. It is not meant to be, but it is an honest one. And honesty, in the face of the universe's actual scale, is the only posture that makes sense. Because the alternative, the comfortable illusion that the sky is full, that the universe is populated, that we are surrounded by a cosmos rich with presence and activity, is not just wrong. It is a distortion that prevents us from seeing what the universe actually is. And what the universe actually is something far stranger, far emptier, and far more consequential than the night sky suggests. That something else divides, roughly, into two categories. The first is dark matter, which accounts for approximately 26.8% of the universe's total energy content. The second is dark energy, which accounts for approximately 68.3%. These are not small corrections to an otherwise well-understood picture. They are the dominant components of the universe. The universe is, by composition, mostly things we cannot see, cannot touch, cannot directly detect, and do not fundamentally understand. The visible universe, the part that glows, the part that emits or reflects light, the part that our telescopes can actually observe, is a thin, luminous skin stretched over a vast, dark interior. Dark matter was not discovered by looking for it. It was discovered by noticing that the universe was not behaving the way it should, if only visible matter existed. The first clear signals came from galaxies themselves. When astronomers measured the rotation of spiral galaxies, the speed at which stars and gas at different distances from the galactic center were orbiting, they found something that made no sense under the known laws of gravity. Stars at the outer edges of galaxies were moving too fast, far too fast. According to the distribution of visible matter, the stars and gas that could be seen and measured, the gravitational pull at the outer edges of a galaxy should be relatively weak, and stars there should be orbiting slowly, the way the outer planets of our solar system orbit the sun more slowly than the inner ones. But they were not orbiting slowly. They were orbiting at roughly the same speed as stars much closer to the galactic center. The rotation curves of galaxies were flat when they should have been declining. There were two possible explanations. Either the laws of gravity were wrong, which was not impossible but which would require a fundamental revision of physics that had been tested and confirmed in countless other contexts, or there was more matter in these galaxies than could be seen. Matter that did not emit light, did not reflect light, did not interact with light in any way that made it visible to our instruments, but that still had mass and therefore still exerted gravitational influence. Matter that was there, in enormous quantities, but that was effectively invisible to every telescope ever built. The evidence for this invisible matter accumulated from multiple independent directions. The way galaxy clusters bend light, a phenomenon called gravitational lensing, in which the gravity of a massive object curves the path of light passing near it, revealed that galaxy clusters contained far more mass than their visible components could account for. The way galaxy clusters formed and evolved over cosmic time matched theoretical predictions only if enormous quantities of invisible matter were included in the models. The pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the early universe, the oldest light we can observe, encoded information about the relative amounts of ordinary matter and dark matter in the early universe, and the pattern matched the dark matter hypothesis with remarkable precision. Dark matter is real. The evidence for its existence is overwhelming, coming from so many independent lines of observation that dismissing it would require dismissing most of modern cosmology simultaneously. But what dark matter actually is, what kind of particle or particles it consists of, how it was produced, what its fundamental properties are, remains unknown. Decades of experiments designed to detect dark matter particles directly, to catch them interacting with ordinary matter in underground detectors shielded from cosmic rays, have produced no confirmed detections. Experiments at particle accelerators designed to produce dark matter particles in high-energy collisions have found no clear evidence of them. Dark matter is everywhere. It outweighs ordinary matter by roughly 5 to 1, and yet it has never been directly observed. It is the most abundant form of matter in the universe, and we do not know what it is, but it goes deeper. Because dark matter is not just an invisible component of galaxies. It is the scaffold on which the entire visible universe is built. The cosmic web, the filaments and walls and nodes where galaxies cluster, does not trace the distribution of ordinary matter. It traces the distribution of dark matter. The ordinary matter, the luminous stuff, has simply fallen into the gravitational wells that dark matter created. The galaxies are not the structure, they are the decoration on the structure. The real architecture of the universe is dark, invisible, and detectable only through its gravitational influence on the things we can see. Imagine the cosmic web as a vast three-dimensional mesh of dark matter, a skeleton of invisible mass stretching across the observable universe, with filaments and nodes and sheets of dark matter defining the large-scale geometry of space. Ordinary matter, gas, dust, stars, galaxies, has flowed along this skeleton over billions of years, pooling at the nodes where dark matter is most concentrated, streaming along the filaments, and draining away from the voids where dark matter is sparse. The cosmic web of galaxies that astronomers map is, in this picture, a luminous tracing of an underlying dark structure, a shadow cast by something we cannot see directly, and the voids, those enormous hollow chambers that dominate the volume of the universe, are not simply regions where ordinary matter is absent, they are regions where dark matter is also sparse. The gravitational evacuation that emptied the voids of galaxies also emptied them of dark matter, as the invisible scaffold was itself drawn toward the surrounding filaments and walls. The voids are not just empty of light, they are empty of the very framework that generates structure. They are regions where the universe's skeleton is thin, where the gravitational architecture is weak, where the forces that build and organize matter have largely withdrawn. They are, in the deepest sense, the universe's abandoned territories. But even in these abandoned territories, something remains, and that something is not dark matter. It is something stranger, something that does not cluster with matter, something that does not respond to gravity in the way matter does, something that is, as far as we can tell, perfectly uniform, spread evenly across all of space, inside the voids and outside them, in the densest galaxy clusters and in the most thoroughly evacuated supervoids. This is dark energy, and its relationship to the voids is not incidental. It may be the key to understanding why the voids exist at the scale they do, and why the universe is structured the way it is. Dark energy was discovered in 1998 when two independent teams of astronomers were studying a particular type of exploding star, a type Ia supernova, that can be used as a standard candle, a light source of known intrinsic brightness that allows astronomers to measure cosmic distances with precision. The teams were using these supernovae to map the expansion history of the universe, expecting to find that the expansion was slowing down over time, as gravity gradually braked the outward motion of matter. What they found instead was the opposite. The expansion of the universe was not slowing down, it was speeding up. The universe was not decelerating under the influence of gravity, it was accelerating. Something was pushing space apart faster and faster with each passing billion years. That something was named dark energy, and the discovery earned its finders the Nobel Prize in Physics in 2011. But the name is almost misleading in its simplicity, because dark energy is not energy in any conventional sense. It is not a fuel being burned. It is not a force being applied. It is, as best we can tell, a property of space itself, a tendency of empty space to expand, built into the fabric of the universe at a level so fundamental that it cannot be switched off or redirected. Every cubic meter of space, whether inside a galaxy or inside a void, contains a small but non-zero amount of dark energy, and as the universe expands and space increases in volume, the total amount of dark energy increases with it. Unlike matter, which dilutes as the universe grows larger, dark energy maintains a constant density. It does not thin out, it does not weaken, it grows. This is the mechanism of cosmic acceleration. As the universe expands, the total amount of dark energy increases. As the total amount of dark energy increases, the expansion accelerates further. As the expansion accelerates, the universe grows larger faster, creating more space, which contains more dark energy, which drives further acceleration. It is a self-reinforcing process with no natural break, no equilibrium point, no end state that involves slowing down. The universe is not coasting toward some distant future of gentle expansion. It is accelerating toward a future of increasingly rapid separation, in which the distances between things grow not just larger, but larger at an ever-increasing rate. Now connect this to the voids. The voids are the regions of the universe where dark energy's influence is most purely expressed. In the dense regions of the cosmic web, the filaments, the clusters, the nodes, gravity competes with dark energy. The gravitational attraction of concentrated matter partially counteracts the expansive tendency of dark energy, holding structures together, preventing them from being torn apart by the accelerating expansion. But inside the voids, where matter is sparse and gravity is weak, dark energy operates almost unopposed. The expansion of space inside a void is not significantly resisted by any gravitational pull. The void expands more freely, more completely, more purely than the surrounding structure. The voids are, in a sense, the regions where dark energy is most fully itself, and this means that the voids are growing, not just because matter is draining out of them toward the surrounding filaments, but because the space inside them is expanding faster than the space in the denser regions. The voids are inflating slowly but relentlessly, driven by the same dark energy that is accelerating the expansion of the universe as a whole. Over billions of years, the voids will grow larger. The filaments between them will grow thinner. The galaxy clusters at the nodes of the cosmic web will become more isolated from each other as the distances between them increase. The universe is not just expanding, it is differentiating, becoming more structured in some ways and more separated in others, as dark energy drives the voids to grow and gravity struggles to hold the remaining structures together. This leads to something more disturbing. Because the acceleration driven by dark energy is not a distant future concern, it is happening now. It has been happening for roughly 5 billion years, since dark energy's influence became dominant over the gravitational pull of matter as the universe expanded and matter diluted, and its effects are already visible in the large-scale structure of the cosmos. The most distant galaxy clusters are receding from us not just because of the initial expansion of the universe, but because dark energy is actively pushing them away, adding to their recession velocity with each passing year. Some of them are already receding faster than the speed of light. This is not a violation of relativity. Nothing is moving through space faster than light. What is happening is that the space between us and those distant galaxies is expanding so rapidly that the total distance is increasing at a rate that exceeds the speed of light. The galaxies themselves are not moving through space at superluminal speeds. The space between us and them is simply growing faster than light can cross it. And this means that the light those galaxies emit today will never reach us. It will travel toward us at the speed of light, but the space it must cross will expand faster than it can traverse, and it will never arrive. Those galaxies have already crossed what cosmologists call the cosmic event horizon, the boundary beyond which no signal, no light, no information of any kind can ever reach us, no matter how long we wait. The cosmic event horizon is one of the most philosophically disturbing concepts in modern cosmology. It is not a physical wall. It is not a place where space ends or where something dramatic happens. It is simply a boundary defined by the relationship between the speed of light and the rate of cosmic expansion. Beyond it, the universe continues. Galaxies exist, stars burn, planets orbit, life may flourish, but none of it can ever communicate with us. None of it can ever send us a signal that will arrive. The information about everything beyond the cosmic event horizon is, from our perspective, permanently inaccessible. Not temporarily inaccessible, not inaccessible with current technology, but inaccessible in principle forever, by the laws of physics as we currently understand them. And the horizon is not fixed, it is shrinking. As dark energy accelerates the expansion of the universe, the cosmic event horizon moves closer to us over time. Galaxies that are currently just inside the horizon, galaxies whose light can still, in principle, reach us, will eventually cross it and disappear from our causal universe. Not physically disappear, not cease to exist, but become permanently unreachable, permanently unknowable, permanently beyond the boundary of what we can ever observe or interact with. The observable universe is not a fixed region, it is a shrinking one, and the shrinking is accelerating. Consider what this means for the long-term future of any civilization that might exist in this universe. Right now, we can observe galaxies billions of light years away. We can study their spectra, measure their distances, map their positions, and use them to reconstruct the history and structure of the cosmos. We can see the cosmic microwave background, the afterglow of the Big Bang, and read in its patterns the initial conditions of the universe. We have access through our telescopes to an enormous volume of cosmic history and cosmic structure. But this access is temporary. It is a window that is closing in roughly 100 billion years, a time so far in the future that it dwarfs the current age of the universe by a factor of roughly 7. The Milky Way and the Andromeda galaxy will have merged, and the resulting galaxy will be gravitationally bound to a small number of other galaxies in what remains of the local group. But all other galaxy groups and clusters currently visible to us across billions of light years will have receded beyond the cosmic event horizon. Their light will no longer reach us. Their existence will be undetectable. Any civilization living in that future galaxy, if such a civilization exists, if intelligence persists across such timescales, will look out at the universe and see only their local group, a small island of galaxies surrounded by darkness. No cosmic web, no distant clusters, no evidence of the large-scale structure that we can see today, no cosmic microwave background, which will have redshifted to wavelengths so long they are effectively undetectable, no record, accessible through observation, of the Big Bang or the early universe or the vast architecture of filaments and voids that defines the cosmos we inhabit. That future civilization, if it exists, will have no way of knowing what we know. It will look at the universe and conclude, reasonably and incorrectly, that the universe is small, static, and composed only of its local galaxy group. It will have no observational evidence for cosmic expansion. It will have no evidence for dark energy. It will have no evidence for the Big Bang. All of that information will have been erased, not by catastrophe, not by destruction, but by distance, by the simple, relentless, accelerating expansion of space, which will have carried the evidence beyond the horizon of what can ever be seen. This is one of the most unsettling implications of dark energy's existence. It means that the universe is not just expanding, it is erasing its own history. The information encoded in the positions and spectra of distant galaxies, the information carried by the cosmic microwave background, the information written into the large-scale structure of the cosmic web, all of it is being carried beyond the horizon, one galaxy at a time, one photon at a time, as the expansion accelerates and the observable universe contracts. We happen to live at a time when this information is still accessible. We happen to live at a moment in cosmic history when the universe is still legible. But that moment is not permanent. It is a window, and the window is closing. Some physicists find this deeply troubling, not just philosophically but scientifically, because it raises a question about the nature of scientific knowledge itself. If the universe is structured in such a way that its own history becomes inaccessible over time, if the evidence for its origin and evolution is systematically erased by its own expansion, then what does it mean to claim that we understand the universe? We understand it now with the evidence currently available, but the evidence is not permanent. It is not archived somewhere safe. It is carried away by the expansion of space, and once it crosses the horizon, it is gone. Not lost in the sense of misplaced, gone in the sense of unreachable by any means forever, but it gets worse. Because the erasure of information is not just a future concern, it is a present one, and it operates not just at the scale of the cosmic horizon, but at the scale of individual objects, individual events, individual moments of cosmic history. The universe is not just losing its distant past to the horizon. It is losing information at every scale, through every process in ways that are still being debated and that touch on some of the deepest unresolved questions in theoretical physics. Consider a black hole, a region of space where gravity is so intense that nothing, not matter, not light, not any signal of any kind, can escape. When matter falls into a black hole, the information it carries, its quantum state, its precise configuration, the details of its history, appears to be lost. The black hole grows slightly more massive, but the specific information about what fell in seems to vanish from the accessible universe. This is the black hole information paradox, and it has occupied some of the most brilliant minds in theoretical physics for decades without resolution. The paradox matters not just for black holes, but for the broader question of whether information is conserved in the universe, whether the total amount of information in the cosmos is fixed, or whether it can be genuinely destroyed. If information can be destroyed, if the universe is not just expanding and cooling but genuinely losing the record of its own past, then the long-term future of the cosmos is not just one of increasing emptiness and decreasing temperature. It is one of increasing amnesia, a universe that forgets itself, a universe in which the past becomes not just inaccessible but genuinely absent, erased at the quantum level by the same processes that generate structure and complexity in the present. A universe that is, in the deepest sense, running down, not just in energy, but in information, in complexity, in the capacity to remember what it once was. This connects to the concept of entropy, which will become increasingly central as we follow the universe toward its far future. Entropy is, in its most general sense, a measure of disorder, or more precisely, a measure of the number of possible microscopic configurations that correspond to a given macroscopic state. A highly ordered system has low entropy. A highly disordered system has high entropy. And the second law of thermodynamics, one of the most robust and universal laws in all of physics, states that in any closed system, entropy tends to increase over time. Order tends to give way to disorder. Structure tends to give way to uniformity. Complexity tends to give way to simplicity. The universe as a whole is moving in one direction, toward higher entropy, toward greater disorder, toward a state of maximum uniformity in which no further change is possible. The cosmic web, with its filaments and voids and galaxy clusters, is a low-entropy structure relative to what the universe will eventually become. The stars burning in those galaxies are converting ordered nuclear fuel into disordered heat and light, increasing the entropy of the universe with every photon they emit. The black holes consuming matter at the centers of galaxies are, according to some theoretical frameworks, the highest entropy objects in the universe, vast repositories of disorder, encoding in their event horizons the maximum possible entropy for a given volume of space, and the expansion of the universe driven by dark energy is carrying everything toward a state of maximum entropy, a state in which matter is so diluted, so cold, so spread out that no further thermodynamic processes are possible, a state called heat death, the final silence. But we are getting ahead of ourselves. The heat death of the universe is a destination, not a present reality. Between now and then, there is an enormous amount of cosmic history still to unfold, a history of dying stars, fading galaxies, evaporating black holes, and the slow, cold dispersal of matter across an ever-expanding void. And to understand that history, we need to understand what is happening to the matter that remains, the ordinary matter, the 4.9%, the luminous skin of the cosmos, as dark energy continues its work and the universe continues its expansion. The galaxies we see today are not permanent. They are not eternal fixtures of the cosmos. They are temporary structures assembled by gravity over billions of years, sustained by the ongoing formation of new stars from clouds of gas and dust, and destined to exhaust their fuel and fade. The Milky Way right now is forming new stars at a rate of roughly 1 to 3 solar masses per year, a modest rate compared to the star-forming galaxies of the early universe, which were producing stars hundreds of times faster. But even this modest rate cannot continue indefinitely. The gas that feeds star formation is a finite resource. It is consumed by the stars that form from it, locked up in stellar remnants when those stars die, and gradually depleted over time. The Milky Way's star-forming days are numbered, not in the near future, not in any time frame that matters to human civilization, but on cosmic timescales. The gas will run out, the star formation will slow, and eventually stop. When star formation stops, the galaxy does not immediately go dark. The stars already formed continue to burn, each on its own timescale determined by its mass. The most massive stars, burning their fuel prodigiously, will exhaust themselves in millions of years. The sun-like stars will burn for billions of years. The smallest stars, the red dwarfs, which are by far the most numerous type of star in the galaxy, will burn for trillions of years, far outlasting everything else. But even the red dwarfs will eventually exhaust their fuel. Even the most patient, most frugal stars will eventually go cold. And when the last red dwarf fades, the galaxy will be populated not by burning stars, but by their remnants. White dwarfs, neutron stars, black holes, cold, dark, silent objects drifting through a galaxy that no longer glows. This is the future that the physics points toward. Not a dramatic explosion, not a sudden end, a slow fading, a gradual dimming. A universe that does not go out with a bang, but with a long, cold, barely perceptible diminishment of light, spread across timescales so vast that the entire current age of the universe would be an imperceptible flicker at the beginning of the story. The emptiness that currently characterizes the voids between galaxies will eventually characterize the galaxies themselves, not because the matter disappears, but because the matter stops shining. The universe will become dark, not because it is destroyed, but because it runs out of the fuel that makes it visible. And all of this, the fading of stars, the growth of voids, the acceleration of expansion, the retreat of galaxies beyond the horizon, the slow increase of entropy toward its maximum, all of it is connected to the emptiness we began with. The voids are not just features of the present universe. They are previews of the future universe. They are regions where the future has already arrived, where matter has already thinned to near nothingness, where dark energy already operates unopposed, where the expansion of space already proceeds without resistance. The voids are the universe's future, expressed in the present, and the future they preview is one of increasing separation, increasing silence, and increasing darkness. We are not at the end of this story. We are somewhere in the middle of it, at a moment of unusual richness, a moment when the universe is still full of burning stars, still structured by the cosmic web, still legible to instruments we have built on a small planet orbiting an ordinary star. But the middle of the story is not the whole story, and the direction the story is moving, the direction that every line of evidence points, is toward the emptiness, toward the void, toward a universe that looks in its far future, less like the sky on a clear night, and more like the interior of the Buddha's void, dark, cold, silent, and vast beyond any scale the human mind was built to hold. The question is not whether this is where the universe is going. The evidence suggests it is. The question is what it means, what it implies about the nature of existence, about the relationship between matter and emptiness, about the significance of the brief, bright, structured moment we currently inhabit. And that question takes us somewhere that physics alone cannot fully answer, into territory where science and philosophy meet at the edge of the observable, at the boundary of the knowable, at the horizon beyond which the universe keeps its deepest secrets. There is a particular kind of loneliness that has no human analog, not the loneliness of an empty room or a quiet night, or the absence of someone you expected to find. Those are loneliness measured against the scale of a human life, a human body, a human sense of what nearness means. The loneliness we are approaching now is measured against the scale of the universe itself. It is the loneliness of a galaxy drifting through expanding space, its nearest neighbors receding beyond the horizon of contact, its light traveling outward into a darkness that grows faster than the light can cross it. It is the loneliness of matter in a universe that is, by every physical measure, moving toward a state in which matter is the exception and emptiness is the rule. To feel the weight of this, you need to follow the expansion not just in space, but in time. Not the expansion happening right now, which is already extraordinary, but the expansion that will have happened in 10 billion years, in 100 billion years, in 1 trillion years, because the universe does not operate on human timescales. It does not operate on geological timescales or even on the timescale of the Earth's existence. The universe operates on timescales so vast that our entire cosmic history, from the Big Bang to this moment, roughly 13.8 billion years, is a brief opening chapter. The story has barely started, and the direction it is heading, written in the physics of dark energy and entropy and the slow exhaustion of stellar fuel, is one that becomes progressively harder to look at directly. Start with the near future, cosmically speaking. In roughly 4 billion years, the Andromeda galaxy, currently approaching the Milky Way at approximately 110 kilometers per second, will begin its merger with our galaxy. This is not a collision in the conventional sense. Galaxies are so sparse, so thoroughly composed of empty space that the individual stars within them will almost certainly not collide with each other. What will happen instead is a gravitational dance, a slow interpenetration of two enormous dark matter halos, a gradual disruption and reshaping of both galaxy structures over hundreds of millions of years, until the two systems merge into a single, larger elliptical galaxy. The cosmic web will not be disrupted by this event. The expansion of the universe will not pause for it. It will simply be two galaxies becoming one, a local gravitational event in a universe that is simultaneously growing larger in every direction. The merged galaxy, sometimes called Milkomeda in informal discussions, though the name is not official, will be gravitationally bound to the other members of the local group. The large and small Magellanic Clouds, the Triangulum Galaxy, the dozens of smaller dwarf galaxies that orbit the Milky Way and Andromeda, all of these will eventually be drawn into the merged system, or will orbit it as satellites. The local group will consolidate. Gravity will hold it together even as dark energy drives everything outside it away. And this is the key dynamic of the far future. Gravity wins locally. Dark energy wins globally. The universe will not be torn apart uniformly. It will fragment into isolated islands, gravitationally bound groups and clusters, separated by ever-growing voids of expanding space. This fragmentation is already underway. The Virgo cluster, the nearest large galaxy cluster to our local group, is currently close enough that its gravitational influence is measurable. It contributes to a slight deviation in the motion of our local group called the Virgo-centric flow. But the Virgo cluster is not gravitationally bound to our local group. The expansion of space between us and the Virgo cluster is sufficient to overcome the gravitational attraction between the two structures. Over the next several billion years, the Virgo cluster will recede from us, slowly at first, then faster as dark energy's influence compounds. Eventually, it will cross the cosmic event horizon and disappear from our observable universe entirely. not destroyed, not gone, simply unreachable, simply beyond the boundary of what can ever be known from our location in space. And the Virgo cluster is just the nearest example. Every galaxy cluster beyond our local group is on the same trajectory. Every structure that is not gravitationally bound to us is being carried away by the expansion of space, accelerating toward the horizon, moving toward a state of permanent inaccessibility. The universe is sorting itself into isolated gravitational islands, each one surrounded by an expanding ocean of dark energy, each one progressively more alone as the horizon closes in and the darkness outside it deepens. Now push further into the future, 100 billion years from now. The local group has fully consolidated into a single large galaxy. All other galaxy groups and clusters have long since crossed the horizon. The universe outside our gravitational island is dark and inaccessible. The cosmic microwave background has redshifted to wavelengths so long that it is effectively undetectable. The large-scale structure of the cosmic web, the filaments, the walls, the supervoids, is invisible, its evidence carried beyond the horizon. Any observer in this future galaxy, looking out at the universe with the most powerful instruments imaginable, would see only their own galaxy and the darkness surrounding it. They would have no way of knowing that the universe was once full of billions of galaxies, no way of detecting the cosmic web, no way of measuring the expansion of space, because the evidence for all of it would be gone. But the stars are still burning. The red dwarfs, those small, cool, extraordinarily patient stars that burn their hydrogen fuel so slowly and so efficiently that they can sustain nuclear fusion for trillions of years, are still shining. The galaxy is dimmer than it once was. The brilliant blue and white stars that once lit the spiral arms have long since exhausted themselves and died. The sun-like stars are gone. Their cores collapsed into white dwarfs that are slowly cooling, but the red dwarfs persist, filling the galaxy with a faint ruddy glow, a twilight that will last far longer than the bright era of stellar formation that preceded it. This era, the long, slow burning of the red dwarfs, is sometimes called the degenerate era in theoretical discussions of the far future, though the name refers to the degenerate matter that will eventually dominate the galaxy, rather than to any moral quality of the epoch. It is an era of extraordinary duration. The longest-lived red dwarfs may burn for 10 trillion years or more, 1,000 times the current age of the universe. During this time, the galaxy will be a quiet, dim, slowly cooling place. Star formation will have ceased. The gas that once fed the birth of new stars will have been consumed or dispersed. The galaxy will be living off its remaining stellar capital, burning down the last of its nuclear fuel in the slow, patient fires of its smallest stars. And then, one by one, the red dwarfs will go out. Not dramatically, not in explosions or supernovae. Red dwarfs are too small and too cool to end their lives violently. They will simply exhaust their hydrogen, contract slightly, and cool. Their surfaces will dim from red to infrared to nothing detectable. They will become black dwarfs, cold, dark, inert spheres of degenerate matter, the size of a planet but the mass of a star, drifting silently through a galaxy that no longer glows. The transition from the last red dwarf to the first black dwarf will not be a moment, it will be a process, spread across trillions of years, a slow extinguishing of the last fires in a universe that was once brilliant with light. It is worth pausing here to note that black dwarfs are theoretical objects. No black dwarf has ever been observed because the universe is not yet old enough for any white dwarf to have cooled to the point of becoming one. The cooling process takes longer than the current age of the universe by many orders of magnitude. Black dwarfs are a prediction of physics, a logical consequence of the known properties of matter, and the known age of the universe's future. They are what white dwarfs become given enough time. And in the far future, the galaxy will be full of them. Cold, dark, silent remnants of stars that once burned, drifting through a space that has forgotten what light was. But it gets worse, because even the black dwarfs are not permanent. Even the cold, inert remnants of dead stars are subject to processes that will, given enough time, dissolve them. One such process is proton decay, a theoretical process in which the protons that make up ordinary matter spontaneously transform into lighter particles, slowly eroding the structure of matter itself. Proton decay has never been observed. Current experiments have established that if it occurs, the proton lifetime must be extraordinarily long, at least 10 to the 34th years, and possibly much longer. But if proton decay occurs at all, and some theoretical frameworks suggest it must, then given enough time, every proton in every black dwarf, every neutron star, every cold rock, every atom of ordinary matter in the universe will eventually decay. The matter will dissolve. not into energy in any useful sense, but into lighter particles, positrons, neutrinos, photons, that will themselves disperse into the expanding void. The timescale for this is almost incomprehensible. 10 to the 37th years, or 10 to the 40th years or longer, depending on the specific theoretical model. These numbers are so large that they make the current age of the universe, 13.8 billion years, or roughly 10 to the 10th years, look like an infinitesimal instant. The universe we currently inhabit, with its galaxies and stars and planets and life, exists in the first few heartbeats of a story that will continue for durations that have no human analog, no earthly comparison, no frame of reference that a mind evolved for savanna survival can genuinely hold. And yet the physics points there, the logic of entropy, the logic of proton decay, the logic of dark energy's relentless expansion, all of it points toward a future in which the matter we know dissolves, the structures we observe disperse, and the universe approaches a state of maximum entropy in which nothing further can happen, not because something destroys it, not because some catastrophe intervenes, but because the universe runs its course, because every process has a timescale, and given enough time, every process completes. The universe is not heading toward destruction, it is heading toward completion, and completion, in thermodynamic terms, looks like silence. But before the protons decay, before the black dwarfs dissolve, there is another process operating on a somewhat shorter timescale, shorter in the sense that it completes in a mere 10 to the 67th years, rather than 10 to the 40th. This is the evaporation of black holes. Black holes, according to a theoretical framework developed by Stephen Hawking in the 1970s, are not perfectly black. They emit a faint thermal radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly lose mass. Over an extraordinarily long time, a black hole will radiate away all of its mass and disappear. The most massive black holes, the supermassive black holes at the centers of galaxies with masses billions of times that of the Sun, will take the longest to evaporate. But they will evaporate, given enough time. Even the most massive black hole in the universe will shrink to nothing, emitting its last faint burst of Hawking radiation and leaving behind only the expanding void. Hawking radiation has never been directly observed. The radiation from stellar mass black holes is so faint, so far below any currently detectable threshold, that confirming it experimentally is beyond any foreseeable technology. But the theoretical framework that predicts it is robust, and most physicists accept it as almost certainly correct. The evaporation of black holes is not a speculation. It is a prediction of quantum mechanics applied to curved spacetime, and it has profound implications for the fate of information in the universe, implications that remain unresolved and that connect to some of the deepest questions in theoretical physics. When a black hole evaporates, what happens to the information it consumed? The matter that fell into the black hole carried information, the precise quantum states of every particle, every atom, every structure that crossed the event horizon. If the Hawking radiation that carries the black hole's mass back out into the universe is truly thermal, truly random, truly carrying no information about what fell in, then the information is destroyed. It is not just inaccessible, it is gone. The universe has genuinely lost a record of its own past, and this would violate a principle that most physicists consider fundamental, the principle that quantum information is conserved, that the total information content of the universe cannot decrease. The resolution of this paradox, if it has a resolution, is one of the most actively pursued problems in theoretical physics. Some physicists argue that the information is encoded in subtle correlations in the Hawking radiation, correlations so complex and so delicate that they are practically undetectable, but theoretically present. Others argue that the information is preserved in some form at the event horizon, encoded in the structure of spacetime itself. Others suggest that the paradox reveals a fundamental incompatibility between quantum mechanics and general relativity that will only be resolved by a deeper theory, a theory of quantum gravity that we do not yet have. The debate is ongoing, the answer is unknown, and the stakes are not trivial because the answer determines whether the universe is, at its deepest level, a place that preserves its own history or a place that erases it. This question, whether the universe preserves or erases information, is not just a technical problem in theoretical physics, it is a question about the nature of reality itself. If information is conserved, then the past is, in some sense, permanent. Every event that has ever occurred leaves an indelible mark on the quantum state of the universe, a mark that cannot be erased, only made increasingly difficult to read. The universe in this picture is a perfect record of everything that has ever happened, even if that record is encoded in a form so complex and so dispersed that it can never be practically accessed. The past exists somewhere in the structure of the present, but if information can be destroyed, if black holes genuinely erase the quantum states of the matter they consume, then the past is not permanent. Events can happen and leave no trace. The universe can forget, and a universe that forgets is a fundamentally different kind of place than a universe that remembers. It is a place where the connection between past and present is not absolute, where the arrow of time points not just toward higher entropy, but toward genuine erasure, where the future is not just different from the past but disconnected from it in a way that undermines the very concept of causality. We do not know which kind of universe we live in. The evidence does not yet decide the question, and this uncertainty, this fundamental unresolved question about whether the universe preserves or destroys its own history, sits at the heart of the deepest problems in modern physics, connecting quantum mechanics, general relativity, thermodynamics, and the philosophy of time in ways that are still being untangled. It is one of the places where the map of human knowledge ends and the territory of the unknown begins, and it is in its own way as disturbing as the voids, because the voids are empty of matter. But a universe that destroys information is empty of something more fundamental. It is empty of its own past. Return now to the expanding universe. Return to the dark energy driving the acceleration, the voids growing larger, the galaxy clusters retreating beyond the horizon. Because there is one more aspect of this picture that has not yet been fully examined, one more implication of the accelerating expansion that connects the large-scale structure of the cosmos to the fate of individual objects, individual moments, individual acts of observation. It is the implication that concerns the Hubble flow, the systematic recession of galaxies driven by the expansion of space, and what it means for the relationship between any observer and the universe they inhabit. The Hubble flow is named after Edwin Hubble, who in the late 1920s established the observational foundation for cosmic expansion by demonstrating that distant galaxies were receding from us and that their recession velocity was proportional to their distance. The further a galaxy, the faster it recedes. This relationship, Hubble's law, is not a consequence of galaxies moving through space away from us. It is a consequence of space itself expanding. Every region of space is growing larger, and the effect accumulates with distance. A galaxy twice as far away recedes twice as fast, because there is twice as much expanding space between us and it. At sufficient distances, the recession velocity implied by the Hubble flow exceeds the speed of light. This is the origin of the cosmic event horizon discussed earlier. But the Hubble flow has another implication that is worth examining carefully. It means that the universe has no center. There is no point in space from which the expansion is emanating, no privileged location from which all other galaxies are receding. Every point in space sees every other point receding from it, in every direction, at a rate proportional to distance. If you were in the Virgo cluster, you would see our local group receding from you. If you were in a galaxy on the opposite side of the observable universe, you would see the same pattern. Every other galaxy receding, the expansion looking the same in every direction, the universe appearing to expand away from you as its center. This is deeply counterintuitive. It feels like it should imply a center, like the expansion should be emanating from somewhere, but it does not. The expansion is a property of space itself, not a motion through space. Space is growing everywhere simultaneously, and the effect is that every point in space is moving away from every other point. The universe has no edge, no center, no preferred location. It is, in the language of cosmology, homogeneous and isotropic on large scales, the same in every direction, the same at every location, at least when averaged over sufficiently large volumes. But this homogeneity is itself a kind of disturbing fact, because it means that our location in the universe is not special. The view from our galaxy, the cosmic web we can map, the voids we can study, the distant galaxies we can observe, is not a privileged view. It is a typical view, and a typical view, in a universe dominated by voids, is a view mostly of emptiness. Most locations in the universe, if you could somehow be transported to them, would offer a view similar to what you would see from inside the Bautas void. Darkness in every direction, the nearest galaxy 100 million light-years away, the cosmic web visible only as a faint pattern at the very edge of what instruments could detect. Most of the universe, from most locations within it, looks like nothing. We are fortunate, in a narrow sense, to be located where we are, inside a galaxy, near the edge of a filament of the cosmic web, close enough to other galaxies to observe them and study them, and use them to reconstruct the history and structure of the cosmos. Our location gives us access to information that most locations in the universe do not provide, but our location is not permanent. The expansion of space is carrying us, along with our galaxy and our local group, into an increasingly isolated position. The information available to us is decreasing, the window of cosmic legibility is closing, and the direction of travel, the direction that physics and thermodynamics and the logic of dark energy all point, is toward the typical condition of the universe, toward the void, toward the darkness, toward the silence that characterizes most of space and that will eventually characterize all of it. There is a concept in thermodynamics called the arrow of time. It refers to the fact that time has a direction, that the past is different from the future, that processes run in one direction and not the other, that entropy increases rather than decreases. The arrow of time is not a fundamental feature of the laws of physics at the microscopic level. The equations of quantum mechanics and general relativity are, in most formulations, time-symmetric. They work equally well in both directions. The arrow of time emerges from the statistical behavior of large numbers of particles, from the overwhelming probability that a system will evolve toward higher entropy, rather than lower. It is a macroscopic phenomenon, a consequence of the universe's initial conditions. The fact that the universe began in an extraordinarily low entropy state and has been evolving toward higher entropy ever since. The Big Bang, in this picture, was not just the beginning of time and space, it was the beginning of the arrow of time. It was the moment at which the universe was set in its lowest entropy initial state, from which all subsequent evolution has been a journey toward higher entropy, toward greater disorder, toward the heat death that waits at the end of the story. Every star that burns, every galaxy that forms, every black hole that consumes matter, every photon that travels through the expanding void, all of it is part of the universe's journey from its extraordinarily ordered beginning toward its maximally disordered end. We are not observers of this journey from outside. We are part of it. We are, in the most literal sense, a temporary low entropy fluctuation in a universe that is moving inexorably toward maximum entropy. We are order in a universe that is becoming disorder. We are structure in a universe that is becoming void. And this is where the philosophical weight of the emptiness becomes fully apparent. The voids are not just large empty spaces. They are not just features of the cosmic web or consequences of gravitational dynamics. They are the future. They are what the universe is becoming. The matter that currently exists in filaments and galaxies and stars and planets is being slowly, relentlessly dispersed by the expansion of space, by the exhaustion of stellar fuel, by the decay of matter itself, into an ever larger volume of ever emptier space. The voids are growing, the matter is thinning, the light is fading, and the direction of travel is clear. Some physicists and philosophers find this trajectory deeply meaningful, in a way that is not comforting, but is honest. The universe began in a state of extraordinary order, a hot, dense, nearly uniform plasma in which the seeds of all future structure were encoded in microscopic quantum fluctuations. From that beginning, gravity and dark energy and the laws of thermodynamics have been working together and against each other to produce the universe we see today, a universe of extraordinary complexity and beauty, of galaxies and stars and planets and life, of minds capable of looking up at the night sky and asking what they see. But this complexity is not the destination. It is a waypoint, a temporary elaboration on the journey from low entropy to high entropy, from order to disorder, from structure to void. The universe did not create complexity as its goal. Complexity emerged as a consequence of the journey, a byproduct of the processes that are carrying the universe toward its final state. Stars form because gravity compresses gas, releasing energy in the process of building order locally while increasing disorder globally. Life emerges because chemistry can, under the right conditions, produce self-replicating structures that temporarily decrease local entropy while increasing the entropy of their surroundings. Intelligence arises because evolution can, under the right conditions, produce nervous systems capable of modeling the world and predicting the future, temporarily concentrating information while dissipating energy into the environment. All of it, every star, every planet, every organism, every thought, is a local, temporary eddy of order in a universe that is flowing toward disorder. Beautiful, perhaps. Remarkable, certainly, but temporary, always temporary, and the emptiness is the reminder of this. The voids are the parts of the universe where the journey is furthest along, where the temporary eddies of order have already dispersed, where the matter has already thinned and the light has already faded, and the silence has already settled. They are not the absence of the universe. They are the universe in its most advanced state, the state toward which everything else is moving, at different rates, on different timescales, but in the same direction. The voids are not the background against which the story of the universe plays out. They are the ending of the story, already written in the present, already visible to anyone willing to look. But there is one more layer to this, one more dimension of the emptiness that has not yet been fully explored. Because the voids are not just large and empty and growing, they are also, in a subtle but profound way, isolated. And isolation, true isolation, the kind that operates at cosmic scales, has implications that go beyond thermodynamics and entropy and the fate of matter. It has implications for the nature of knowledge itself, for the relationship between any mind and the universe it inhabits, for the question of whether the universe is, in any meaningful sense, knowable. Consider the following. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is a sphere, roughly 93 billion light-years in diameter. This is the limit of what we can, in principle, observe. Beyond this boundary, the universe continues, possibly infinitely, possibly in a finite but unbounded geometry, but we cannot see it. We cannot receive signals from it. We cannot know what it contains. The observable universe is not the whole universe. It is a bubble of knowability inside a larger reality that is, by definition, beyond our reach, and the observable universe is shrinking. As dark energy accelerates the expansion of space, the cosmic event horizon, the boundary beyond which signals can no longer reach us, is moving closer. The observable universe is not growing to encompass more of the cosmos as time passes. It is contracting, losing access to regions that were once within reach as the expansion carries them beyond the horizon. The universe is becoming less knowable over time, not more. The window of observation is closing, not opening, and the direction of travel, the direction that every line of evidence points, is toward a future in which the observable universe consists of a single gravitationally bound island of matter, surrounded by an infinite, inaccessible, forever dark expanse of expanding space. This is the deepest form of cosmic isolation, not the isolation of a planet in a solar system, or a solar system in a galaxy, or a galaxy in a cluster. The isolation of an entire gravitationally bound structure, an entire island universe, surrounded by a void so vast and so rapidly expanding that no signal from outside it can ever arrive, and no signal from inside it can ever escape to reach anything beyond. An island of matter in an ocean of expanding space, cut off from the rest of the universe not by distance alone, but by the physics of expansion, by the geometry of space-time, by the relentless work of dark energy on the fabric of the cosmos. And here is the thought that sits at the edge of what the physics implies, the thought that is hardest to hold without a certain vertigo. We may already be in that island. The local group, our galaxy, Andromeda, the Magellanic Clouds, the dozens of smaller galaxies bound to us by gravity, may already be the entirety of what will ever be accessible to any civilization that arises within it, on any timescale, using any technology consistent with the known laws of physics. Everything beyond the local group is already receding. Everything beyond the cosmic event horizon is already gone. The universe we can see today, the billions of galaxies spread across the observable volume, is a temporary gift, a consequence of our position in cosmic time, a view that will not be available to any observer who comes after us by a sufficient margin. We are living in the most information-rich moment our corner of the universe will ever experience. The evidence for the Big Bang is still visible. The cosmic web is still mappable. The distant galaxies are still observable. The expansion of the universe is still measurable. All of this will fade. All of this will be carried beyond the horizon, and what remains in the far future will be an island of matter in a sea of darkness, with no way of knowing what lies beyond, no way of reconstructing the history that has been erased, no way of recovering the information that the expansion has carried away. The universe will have become, for any observer within it, a small, dark, quiet place, not because it has shrunk, but because the rest of it has become unreachable. This is not a comfortable thought. It was not meant to be, but it is an honest one. And honesty in the face of what the physics actually implies requires sitting with the discomfort rather than softening it. The universe is not moving toward a future of greater connection, greater knowledge, greater accessibility. It is moving toward a future of greater isolation, greater darkness, greater silence. The emptiness is not the exception, it is the destination, and we are already on the way. There is a word that physicists use when they want to describe the state of a system that has reached its maximum entropy, its final equilibrium, the condition from which no further change is possible. The word is equilibrium, but equilibrium, in this context, does not mean balance in any peaceful sense. It means the end of difference, the end of gradient, the end of the conditions that make processes possible, that allow energy to flow from one place to another, that permit structure to form and persist, and do anything at all. Equilibrium, at cosmic scales, means the end of everything that could be called happening. It means a universe in which nothing occurs, not because something prevents it, but because there is no longer any difference between one state and another that would drive any process forward. It is not destruction, it is completion. And completion, in thermodynamic terms, is indistinguishable from permanent silence, but we are not there yet. And the journey toward that silence passes through stages that are themselves extraordinary, stages that the physics predicts with remarkable specificity, stages that unfold across timescales that dwarf anything in human experience, but that are nonetheless finite, nonetheless calculable, nonetheless part of the same story that began with the Big Bang and that we are currently living somewhere near the beginning of. To understand where the universe is going, it helps to follow the trajectory not just in broad strokes, but in the specific, sequential unfolding of processes that will shape the far future of matter, energy, and space. The next major transition in the universe's history, after the end of star formation, after the slow cooling of the last red dwarfs, will be the era dominated by the remnants of dead stars. White dwarfs, neutron stars, and black holes will be the primary constituents of galaxies that no longer glow. White dwarfs are the cooling cores of stars like our Sun, dense spheres of carbon and oxygen, roughly the size of Earth but with the mass of a star, supported against gravitational collapse not by nuclear fusion, but by the quantum mechanical pressure of electrons packed so tightly they resist further compression. They cool slowly, radiating their residual heat into the surrounding void, dimming from white to yellow to orange to red to infrared, over timescales of billions and then trillions of years. Neutron stars are the remnants of more massive stars, objects so dense that a teaspoon of their material would weigh billions of tons, objects where the protons and electrons of ordinary matter have been crushed together into neutrons by the force of gravitational collapse. They are supported against further collapse by the quantum pressure of neutrons, and they cool even more slowly than white dwarfs, their surfaces radiating faint X-rays that diminish over time as the star loses its thermal energy to the surrounding space. In the far future, neutron stars will be cold, dark, and nearly undetectable, dense remnants of violent stellar deaths, drifting silently through a galaxy that has forgotten the explosions that created them. And then there are the black holes, the endpoints of the most massive stellar deaths, and the supermassive objects at the centers of galaxies, objects with masses millions or billions of times that of the Sun, objects whose gravitational influence shapes the dynamics of entire galaxies, objects from which nothing escapes. In the era after star formation ends, the black holes will be the most energetically significant objects in the universe. They will continue to grow slowly by consuming the cold remnants of dead stars that wander too close. They will dominate the gravitational landscape of their host galaxies, and they will wait, patient and dark, for the unimaginably long timescales required for Hawking radiation to erode their mass and carry it back into the void. The waiting time for a stellar mass black hole, an object with a mass roughly 10 times that of the Sun, to evaporate completely through Hawking radiation is approximately 10 to the 67th years. For a supermassive black hole with a mass a billion times that of the Sun, the evaporation time is roughly 10 to the 96th years. These numbers are so large that they require a different kind of relationship with time than human intuition provides. The current age of the universe, 13.8 billion years, is 10 to the 10th years. The evaporation time of a supermassive black hole is 10 to the 96th years. The ratio between these two numbers is itself a number so large that writing it out in full would require more digits than there are atoms in the observable universe. And yet, given enough time, the black holes will evaporate. The Hawking radiation will carry their mass away, photon by photon, in a process so slow that the rate of energy loss is effectively unmeasurable by any current instrument. The final moments of a black hole's evaporation, when its mass has been reduced to a tiny fraction of its original value, and the Hawking radiation becomes intense enough to be dramatic, will be a brief, brilliant burst of energy, a last flash of light in a universe that has otherwise gone dark, and then silence. The black hole will be gone. The matter it consumed will have been converted through the slow alchemy of Hawking radiation into a diffuse spray of particles and photons dispersed into the expanding void. The information it contained, if information is preserved, if the paradox is resolved in favor of conservation, will be encoded in correlations so subtle and so dispersed that recovering it would be, for any practical purpose, impossible. After the last black hole evaporates, the universe will enter a phase that has no precedent in its history, a phase in which the dominant constituents of matter, if proton decay occurs, are not atoms or molecules or stellar remnants, but the decay products of protons, positrons, electrons, neutrinos, and photons, all dispersed into an expanding void at temperatures so close to absolute zero that the difference is academic. If proton decay does not occur, if protons are genuinely stable, as some theoretical frameworks suggest, then the universe will be populated by black dwarfs and neutron stars and the occasional black hole, all cooling toward absolute zero, all drifting apart as the expansion of space carries them to ever greater separations. Either way, the universe will be dark. Either way, the universe will be cold. Either way, the universe will be approaching the state of maximum entropy from which no further change is possible. This is the heat death, not a dramatic event, not a moment of destruction or transformation, simply the final approach to equilibrium, the slow, cold, dark settling of the universe into a state of maximum disorder, from which it cannot escape, and from which no process can extract any useful work. The heat death is not a wall the universe hits. It is a condition the universe approaches asymptotically, getting closer and closer without ever quite arriving, the last faint processes becoming slower and slower, the last faint temperature gradients becoming smaller and smaller, until the universe is, for all practical purposes, in its final state, uniform, cold, dark, silent, infinite in extent perhaps, but empty of anything that could be called an event. And here is the thought that the heat death forces upon anyone willing to follow it to its conclusion. If the universe reaches heat death, if the final state of the universe is a cold, dark, maximally disordered expanse of expanding space, then the entire history of the universe, from the Big Bang to the last evaporating black hole, will have been a temporary fluctuation, a brief extraordinary elaboration of structure and complexity and light, arising from an extraordinarily low entropy initial condition and dissipating, over unimaginable timescales, into the featureless equilibrium that thermodynamics demands. The stars, the galaxies, the planets, the life, the minds, all of it will have been a parenthesis, a temporary deviation from the universe's default state, which is emptiness. But it goes deeper, because the heat death is not just the end of the universe's story. It is, in a sense, the revelation of what the universe's story was always about. The universe began in a state of extraordinarily low entropy, a state so ordered, so precisely configured, that the probability of it arising by chance from a higher entropy background is effectively zero. The origin of this low entropy initial condition is one of the deepest unsolved problems in cosmology. Why did the universe begin in such an ordered state? What set the initial conditions? What determined the extraordinarily precise configuration of matter and energy and space-time that gave rise to the Big Bang and everything that followed? One possibility, and it is a possibility that some physicists find compelling, though it remains deeply speculative, is that the low entropy initial condition of our universe is not unique. That the universe we inhabit is one of an enormous number of universes, each with different initial conditions, each evolving according to the same or different laws of physics, each reaching its own version of heat death on its own timescale. In this picture, sometimes called the multiverse, our universe's extraordinarily ordered beginning is not a mystery requiring explanation. It is a selection effect. Among the vast ensemble of possible universes, only those with sufficiently ordered initial conditions can give rise to the complexity required for observers to exist. We find ourselves in an ordered universe, not because ordered universes are common, but because disordered universes cannot produce observers to notice their disorder. This is the anthropic principle, applied to cosmology, and it is either a profound insight or a profound evasion, depending on your philosophical disposition. It explains the low entropy initial condition of our universe by appealing to the existence of other universes that we cannot observe, cannot test, and cannot falsify. It replaces one mystery, why did our universe begin in such an ordered state, with another mystery, why does the multiverse exist and what determines the distribution of initial conditions across it? It is not a satisfying answer, but it may be the honest one, because the alternative, Claiming that our universe's initial conditions were specially chosen, or that they arose from some deeper principle we have not yet discovered, requires either a leap of faith or a theory we do not yet have. The evidence does not decide this question. The multiverse, if it exists, is by definition beyond the observable universe, beyond the cosmic event horizon, beyond any possible observation or test. It is a theoretical construct, motivated by the logic of certain inflationary models and certain interpretations of quantum mechanics, but not directly supported by any observation. Some physicists regard it as a legitimate scientific hypothesis. Others regard it as metaphysics dressed in the language of physics. The debate is ongoing, and the answer, if there is one, lies beyond the current reach of science. But set the multiverse aside. Return to the universe we can observe, the universe we inhabit, the universe whose fate the physics describes with increasing specificity as we follow it forward in time. Because there is one more aspect of the far future that has not yet been addressed, one more implication of the accelerating expansion and the growing isolation of gravitationally bound structures that connects the large-scale fate of the universe to the question of what it means for anything to exist within it. Consider the following scenario. A civilization arises somewhere in the far future, in the merged galaxy that was once the Milky Way and Andromeda. This civilization is extraordinarily advanced, capable of harnessing the energy of stars, of manipulating matter at the quantum level, of building structures and conducting experiments on scales that dwarf anything in human history. It has access to all the matter and energy within its gravitationally bound island. It can study the physics of its local environment with extraordinary precision, but it cannot reach beyond its island. The expansion of space has carried everything else beyond the horizon. The cosmic microwave background has redshifted to undetectable wavelengths. The evidence for the Big Bang is gone. The evidence for the cosmic web is gone. The evidence for dark energy, which can only be measured by observing the recession of distant galaxies, is gone because there are no distant galaxies to observe. This civilization, for all its sophistication, inhabits a universe that appears to consist of a single galaxy surrounded by infinite darkness. It has no way of knowing that the universe was once full of billions of galaxies. It has no way of knowing that the cosmic web existed. It has no way of knowing that the expansion of space is accelerating, because the only evidence for that acceleration, the recession of distant galaxies, has been erased by the very process it would need to measure. It may develop a cosmology. It may construct theories about the origin and nature of the universe, but those theories will be built on a fraction of the evidence available to us today, and they will be wrong in ways that the civilization cannot know, because the evidence that would correct them is permanently inaccessible. This is one of the most philosophically disturbing implications of dark energy's existence. It means that the universe is structured in such a way that the truth about its nature becomes progressively less accessible over time. The universe is not just expanding, it is hiding itself. The evidence for its own history is being systematically removed from the reach of any observer, carried beyond the horizon by the same expansion that defines the universe's large-scale behavior. We happen to live at a moment when the evidence is still available, when the cosmic microwave background is still detectable, when distant galaxies are still observable, when the expansion of space is still measurable. But this moment is not permanent. It is a window, and the window is closing faster than we might like to think. Some cosmologists have described our current era as a golden age of cosmology, a period in which the universe is maximally legible, in which the evidence for its origin and evolution is still accessible, in which the tools of observation and the laws of physics align to make the universe's history readable. This golden age will not last. The evidence is being erased. The window is closing. And the civilizations that come after us, or if any do, will inherit a universe that is darker, quieter, and less informative than the one we currently inhabit. They will look out at the darkness and see less than we see. They will ask the same questions we ask, and they will have fewer tools with which to answer them. There is something in this that feels like a kind of cosmic tragedy. Not in the sentimental sense. The universe does not have intentions, does not experience loss, does not mourn the erasure of its own history. But in the structural sense, the universe is arranged in such a way that knowledge of its nature is a temporary condition, available only to observers who exist at the right moment in cosmic time, and that moment is passing. We are living in it. We are right now in the brief window during which the universe is most knowable, and the window is closing. But it gets worse. Because the erasure of cosmological evidence is not the only way the universe is becoming less knowable. There is also the question of what happens to the matter that remains. The cold remnants of dead stars, the dispersed products of proton decay, the faint radiation of evaporating black holes, as the universe approaches heat death. Because as the universe approaches maximum entropy, the distinction between one configuration of matter and another becomes increasingly meaningless. The universe becomes increasingly uniform, and a uniform universe is, in a precise thermodynamic sense, a universe that contains no information. Not because information has been destroyed, but because information requires difference, requires the distinction between one state and another, and in a maximally uniform universe, there are no differences left to encode information in. This is the deepest form of the universe's self-erasure, not the loss of specific facts about specific events, not the erasure of the cosmic microwave background or the recession of distant galaxies, but the loss of the capacity for information itself. A universe at maximum entropy is not just a universe that has forgotten its past. It is a universe that can no longer remember anything because the physical substrate required for memory, the differences, the gradients, the structures that encode information, no longer exists. It is a universe that has become, in the most literal sense, thoughtless. Not because thought has been destroyed, but because the conditions for thought, the conditions for any process that could be called information processing, have been thermodynamically exhausted. And this connects back to the voids, because the voids are, in a sense, a preview of this condition. Inside a deep void, the density of matter is so low, the temperature so close to the cosmic background, the gradients so shallow, that the conditions for complex processes are nearly absent. The void is not a place where things happen. It is a place where things have stopped happening or never started. It is a region of the universe that has, in its own local way, approached something like thermodynamic equilibrium, not the final equilibrium of heat death, but a local approximation of it, a region where the universe's tendency toward uniformity has run further than in the surrounding structure. The voids are the universe's future, expressed in the present. They are the regions where the arrow of time has, in a local sense, run out of things to point at. They are the regions where the universe has already become, in miniature, what it will eventually become everywhere: cold, dark, uniform, and silent. And they are growing. The voids are growing, and the matter is thinning, and the light is fading, and the universe is moving, slowly, relentlessly, on timescales that dwarf human comprehension, toward the condition that the voids already embody. There is a question that this trajectory forces, a question that sits at the intersection of physics and philosophy, and that has no clean answer within the framework of either discipline alone. If the universe began in a state of extraordinary order and is moving toward a state of maximum disorder, if the entire history of the cosmos is a journey from low entropy to high entropy, from structure to void, from complexity to uniformity, then what is the significance of the complexity that arises along the way? What is the significance of the stars, the galaxies, the planets, the life, the minds? Are they meaningful features of the universe's story, or are they incidental byproducts of the thermodynamic journey, temporary eddies of order that arise and dissolve without leaving any permanent mark on the universe's final state? Physics, strictly speaking, does not answer this question. Physics describes the trajectory. It does not assign significance to the waypoints. The laws of thermodynamics do not distinguish between a universe that produces minds and a universe that does not. The second law of entropy does not care whether the low-entropy structures that form along the way are stars or galaxies or living organisms or civilizations. It only cares about the direction of the journey, and the direction is always the same, toward higher entropy, toward greater disorder, toward the final equilibrium. The significance of the complexity, if it has any, is not written in the physics. It is written, if anywhere, in the minds that arise from the complexity and ask the question. And this is perhaps the most unsettling implication of all. Not that the universe is empty, or that it is becoming emptier, or that the evidence for its history is being erased, or that the final state of everything is cold silence. All of those are disturbing, but they are disturbing in a way that can be held at arm's length, examined as facts about a universe that is large and indifferent and operating according to laws that do not require our approval. What is harder to hold at arm's length is the implication that the significance of everything, of every star that burned, every planet that formed, every organism that lived, every mind that wondered, is not a feature of the universe, but a feature of the wondering. That meaning is not something the universe contains. It is something minds project onto a universe that is, at its deepest level, indifferent to whether they exist or not. This is not a new thought. Philosophers and scientists have grappled with it for centuries, in various forms, under various names. But the cosmological picture we have been building, the picture of a universe dominated by voids, driven by dark energy toward accelerating expansion, moving toward heat death on timescales that make human history invisible, gives this thought a new weight, a new specificity, a new kind of evidence, because the universe is not just abstractly indifferent, it is specifically, physically, measurably moving toward a state in which the conditions for complexity, for life, for mind, for meaning, are progressively less available. The universe is not just indifferent to us, it is, in a thermodynamic sense, moving away from us, moving toward a state in which we, and everything like us, are not just absent, but impossible. And yet, here we are, in the brief, bright, structured moment, in the golden age of cosmological legibility, in the window between the Big Bang and the heat death, during which the universe is complex enough to produce minds, and those minds are capable of looking up at the night sky and asking what they see. Here we are, in the middle of the story, surrounded by evidence of the beginning and pointed toward the end, capable of understanding, at least partially, at least approximately, the trajectory of the universe we inhabit. Here we are, temporary eddies of order in a universe flowing toward disorder, asking questions that the universe itself cannot answer, finding meaning in a cosmos that does not provide it, building knowledge in a universe that is systematically erasing the evidence on which knowledge depends. There is something in this that is not just disturbing, but also in a way that is difficult to articulate, remarkable, not comforting, not reassuring, but remarkable. Because the fact that the universe produces, even temporarily, even locally, even in the face of the thermodynamic tide, structures capable of asking these questions, structures capable of mapping the cosmic web and measuring the expansion of space and calculating the evaporation time of black holes and contemplating the heat death of the universe, is itself an extraordinary fact about the universe, not a fact that changes the trajectory, not a fact that softens the ending, but a fact that is worth holding in the brief window during which it is true. The emptiness is real, the voids are real, the acceleration is real, the horizon is real, the heat death is real, or as close to real as a theoretical prediction can be without direct confirmation. The universe is moving towards silence, and the silence is not metaphorical. It is physical. It is thermodynamic. It is written in the laws of nature with the same authority as the laws of motion, and the laws of electromagnetism, and the laws of quantum mechanics. The silence is coming. The only question is what we do with the window we have, the brief, extraordinary, cosmologically improbable window during which the universe is still legible, still complex, still capable of producing minds that can look into the darkness and ask what it means. We are not at the end of this story yet. There is one more descent to make, one more layer of the emptiness to explore, one more implication of the cosmic trajectory to follow to its conclusion, because the heat death and the evaporation of black holes and the decay of protons are the physical endpoints of the universe's story. But there is a philosophical endpoint that lies beyond them, a question about the nature of the silence itself, about what it means for the universe to reach its final state, about whether the concept of existence retains any meaning in a universe that has exhausted all the conditions for change. And that question, followed honestly and without flinching, leads somewhere that is harder to look at than any void, darker than any supervoid, more disturbing than any calculation of cosmic timescales. It leads to the question of what remains when everything that can happen has happened, and the universe has nothing left to do but be. What remains when everything that can happen has happened? The question sounds like philosophy. It sounds like the kind of question that belongs in a seminar room, written on a chalkboard, debated by people who have the luxury of treating the end of the universe as an abstract problem. But it is not abstract. It is physical. It is the logical terminus of the trajectory we have been following, the trajectory that begins with the Big Bang and ends with the heat death, the trajectory that passes through the formation of galaxies and the burning of stars and the growth of voids and the evaporation of black holes and the decay of protons and the final dispersal of matter into an expanding void of maximum entropy. What remains at the end of that trajectory is not nothing in the philosophical sense. It is something specific, something that the physics describes at least approximately, at least in outline. And what it describes is more disturbing than nothing, because it is a kind of existence that has lost all the properties that make existence recognizable. Imagine the universe at a time so far in the future that the number of years elapsed cannot be written in standard notation without using exponents of exponents. The last black hole has evaporated. The last proton has decayed if proton decay occurs. The last white dwarf has cooled to within a fraction of a degree of absolute zero. The expansion of space has carried every gravitationally bound structure so far from every other that the distance between them is not just large but effectively infinite. Infinite in the sense that no signal, no particle, no influence of any kind can ever cross it. Not because the speed of light is insufficient, but because the space between them is growing faster than light can traverse it, and has been doing so for so long that the separation is, for all physical purposes, absolute. The universe is not empty in the way a room is empty when the furniture has been removed. It is empty in the way that a concept becomes empty when every instance of it has been exhausted, when the word no longer points to anything, when the category has no members, when the map describes a territory that no longer exists. In this final state, the universe is populated, if that word can still be used, by a diffuse, extraordinarily cold gas of photons and neutrinos, and if proton decay does not occur, by the cold remnants of dead stars separated by distances so vast that they will never interact again. The temperature of this gas is not zero. Absolute zero is a limit that thermodynamics approaches, but never reaches. The temperature is some positive number so close to zero that the difference is, for any practical purpose, meaningless, but it is not zero, and this matters because a universe at a temperature above absolute zero is, in principle, a universe in which quantum fluctuations still occur, a universe in which the vacuum is still restless, still flickering, still producing the microscopic variations that characterize the quantum vacuum at any non-zero temperature, and this is where the physics leads to something that is either deeply reassuring or deeply disturbing, depending on how you hold it. Because in a universe at maximum entropy, a universe that has reached thermodynamic equilibrium, a universe in which no macroscopic process is possible, the quantum vacuum does not stop fluctuating. The microscopic restlessness of space does not cease, and given enough time, given the kind of time that makes the evaporation time of a supermassive black hole look like an instant, those quantum fluctuations will, purely by chance, produce configurations of matter and energy that are locally ordered, configurations that represent a temporary decrease in local entropy, a brief, spontaneous emergence of structure from the featureless background of maximum disorder. This is the concept of a Boltzmann brain, named after the 19th century physicist Ludwig Boltzmann, who first grappled seriously with the statistical implications of thermodynamics and the arrow of time. The idea is this: in a universe at maximum entropy, the probability of any specific ordered configuration arising spontaneously from random fluctuations is extraordinarily small. But in a universe that persists for an extraordinarily long time, a universe that has been at or near maximum entropy for durations that make the current age of the universe look like a Planck time, even extraordinarily small probabilities become certainties, given enough time. Every possible configuration of matter and energy will eventually arise, purely by chance, from the random fluctuations of the quantum vacuum, including in principle a configuration that constitutes a functioning brain, a structure complex enough to have a momentary experience, a single thought, a single perception, a single instant of awareness, before dissolving back into the featureless background of maximum entropy. A Boltzmann brain, a mind that arises not from the slow, patient process of stellar evolution and planetary formation and biological evolution, but from a random quantum fluctuation in a universe that has otherwise exhausted all its ordered structure. A mind that exists for an instant in isolation, surrounded by nothing but the cold, dark, maximally disordered expanse of a universe that has long since forgotten what stars were. The Boltzmann brain is not a prediction that physicists take seriously as a description of what will actually happen. It is a reductio ad absurdum, a thought experiment that reveals a tension in the foundations of statistical mechanics and cosmology. If the universe persists long enough, and if the laws of quantum mechanics continue to operate, then Boltzmann brains will arise more frequently than ordinary observers like us, observers who arise from the slow, structured process of cosmic evolution. And if Boltzmann brains are more common than ordinary observers, then any given observer is more likely to be a Boltzmann brain than an ordinary observer. But we do not experience ourselves as Boltzmann brains. We experience ourselves as embedded in a coherent, structured universe with a consistent past and a predictable future. This suggests either that the universe does not persist long enough for Boltzmann brains to dominate, or that the laws of physics prevent them from arising, or that our cosmological model is missing something important. The Boltzmann brain problem is not solved. It is one of the open questions at the intersection of cosmology, statistical mechanics, and the philosophy of mind, but it points to something important about the nature of the universe's final state, something that goes beyond the technical details of quantum fluctuations and thermodynamic equilibrium. It points to the fact that the final state of the universe is not simply empty, it is not simply silent. It is a state in which the distinction between existence and non-existence becomes philosophically unclear, a state in which the universe persists, in the sense that space continues to expand, quantum fluctuations continue to occur, the laws of physics continue to operate, but in which nothing that could be called an event, in any meaningful sense, takes place. A state that is, in the deepest sense, indistinguishable from nothing except that it is not nothing. It is something. It is the universe. It is just the universe with nothing left to do. This is the final form of the emptiness, not the emptiness of the Boyuta's void, which is empty of matter but full of expanding space and dark energy, and the faint gravitational influence of the surrounding cosmic web, not the emptiness of the far future galaxy, which is empty of burning stars, but still populated by cold remnants and still subject to the slow processes of gravitational dynamics. The final emptiness is the emptiness of a universe that has completed its thermodynamic journey, that has exhausted every gradient, consumed every source of order, dispersed every structure into the featureless background of maximum entropy, and that continues to exist in a technical sense without containing anything that could be called a difference, a universe that is, in every direction, the same, a universe that has become, in the most literal sense, a void, and the expansion continues. Even in this final state, the expansion of space driven by dark energy does not stop. There is no mechanism in the known physics that would halt it. The universe continues to grow, continues to stretch, continues to increase in volume, even as the matter within it becomes more and more dilute, more and more cold, more and more indistinguishable from the vacuum itself. The expansion is not a process that requires matter to operate. It is a property of space itself, driven by the dark energy that is built into the fabric of the universe at a level more fundamental than any particle or field. Space will continue to expand after the last proton has decayed and the last black hole has evaporated, and the last photon has redshifted to a wavelength longer than the observable universe. Space will continue to expand into a future so remote that the concept of time itself becomes questionable, not because time ends, but because time requires change to be meaningful, and in a universe at maximum entropy, there is no change left to mark its passage. This is the thought that sits at the very edge of what the physics implies, the thought that is hardest to hold without a certain vertigo. Time, as we experience it, is not just the ticking of a clock. It is the unfolding of change, the progression from one state to another, the arrow that points from past to future, the sequence of events that constitutes a history. In a universe at maximum entropy, there are no events. There is no sequence. There is no progression from one state to another, because all states are equivalent, because the universe has reached the condition in which every possible configuration is equally probable, and no configuration is preferred over any other. In such a universe, the concept of time does not disappear. The laws of physics still operate, the quantum vacuum still fluctuates, but time becomes, in a profound sense, meaningless. It passes, but nothing marks its passage. It flows, but there is nothing to flow through. It continues, but there is nothing to continue toward. Some physicists and philosophers have suggested that this final state, the heat death, the maximum entropy, the cold, dark silence of a universe that has exhausted its thermodynamic potential, is not just the end of the universe's story, but the revelation of what the universe fundamentally is. That the low entropy beginning, the structured middle, the complex and luminous era of stars and galaxies and life and mind, all of it is a deviation from the universe's natural state, which is the featureless equilibrium of maximum entropy. That the Big Bang was not the beginning of something new, but the imposition of an extraordinarily improbable initial condition on a system whose natural tendency is toward disorder. That the universe we inhabit, the universe of galaxies and voids and dark matter and dark energy and burning stars and living planets, is not the universe in its normal state. It is the universe in an extraordinarily abnormal state, a state so far from equilibrium that it has produced, as a byproduct of its return to equilibrium, everything we have ever known or imagined. If this is true, and the physics does not prove it, but the logic of thermodynamics points toward it, then the emptiness is not the exception. The emptiness is the rule. The structure is the exception. The light is the exception. The complexity is the exception. The life is the exception. The mind is the exception. Everything that makes the universe recognizable, everything that makes it interesting, everything that makes it the kind of place that can be studied and wondered at and described in a script like this one, all of it is a temporary deviation from the universe's default condition, which is void, which is silence, which is the cold, dark, featureless equilibrium that the universe is always moving toward, and that it will, given enough time, inevitably reach. And the voids we began with, the Botas void, the supervoids, the enormous hollow chambers of the cosmic web, are not just features of the present universe. They are not just consequences of gravitational dynamics and dark energy and the large-scale structure of the cosmos. They are previews. They are the universe showing us in the present what it will eventually become everywhere. They are the regions where the future has arrived early, where the thermodynamic journey has run further than in the surrounding structure, where the universe has already become, in miniature, what it will eventually become in total. The voids are the universe's destination expressed in its present geography. They are the ending written into the middle of the story. Stand at the edge of the Botas void again. Look inward. 330 million light-years of near-nothingness in every direction. No galaxies, no stars, no planets, no light. Just space, expanding, cold, dark, and silent. Just the quantum vacuum, flickering at scales too small to see, in a region too empty to matter. Just dark energy, doing its patient, relentless work of pushing space apart, growing the void larger with each passing year, each passing century, each passing billion years. This is not a place where the universe has failed to produce something. This is a place where the universe has succeeded in becoming what it is always trying to become. This is the universe in its preferred state. This is what everything is moving toward. And now pull back further. Pull back until the Botas void is just one of thousands of similar structures visible in the large-scale map of the cosmos. Pull back until the cosmic web, the filaments and walls and nodes where galaxies cluster, is visible as a thin, luminous tracery stretched across an enormous volume of space, most of which is void. Pull back until the entire observable universe is visible, a sphere 93 billion light-years across, containing hundreds of billions of galaxies arranged in a pattern that is, at its largest scales, mostly empty, mostly void, mostly the universe in its preferred state, with thin threads of matter clinging to the boundaries of enormous hollow chambers, burning briefly in the cosmic night, before the expansion carries them apart, and the entropy carries them down, and the silence claims them one by one. This is the universe, not the universe of the night sky, which is a local, temporary, misleading impression of a cosmos that is mostly empty, and mostly dark, and mostly silent. The actual universe. The universe as it is at the scales where its true nature is visible. A universe of voids, threaded with matter, driven by dark energy toward an accelerating expansion that will eventually isolate every gravitationally bound structure in its own island of space, surrounded by an ever-growing ocean of emptiness, moving toward a final state of maximum entropy, in which the distinction between existence and non-existence becomes, for all practical purposes, academic. The question that this picture forces, the question that the physics raises and cannot answer, the question that sits at the boundary between science and philosophy, and that every mind capable of asking it must eventually confront, is not whether this is true. The evidence points strongly toward it being true, or at least toward it being the best description of the universe's trajectory that our current understanding can provide. The question is what it means. What it means that the universe is structured this way. What it means that the default condition of reality is void. What it means that the complexity and the light and the life and the mind are temporary, local, thermodynamically improbable deviations from a background of emptiness that is always present and always growing and always waiting. There is no answer to this question that the universe provides. The universe does not explain itself. It does not justify its structure or apologize for its trajectory or offer comfort to the minds it temporarily produces. It simply is what it is, a vast, mostly empty, accelerating, cooling, darkening system of matter and energy and space, moving according to laws that do not require our understanding or our approval, toward a destination that does not require our presence. The universe is not hostile to us. It is not indifferent to us in the way a person can be indifferent to another person. It is indifferent to us in the way that a physical process is indifferent to the objects it acts upon, completely, structurally, without exception or variation, and yet the minds it produces, the temporary, thermodynamically improbable, cosmologically insignificant minds that arise in the brief bright window between the Big Bang and the heat death, are capable of knowing this, capable of measuring the expansion of space and mapping the cosmic web, and calculating the evaporation time of black holes, and contemplating the heat death of the universe, capable of looking into the Bode's void and understanding, at least approximately, what they are looking at, capable of following the logic of dark energy and entropy, and the arrow of time to its conclusion, and sitting with the discomfort of what that conclusion implies. This capacity, the capacity for a temporary eddy of order in a universe flowing toward disorder to understand the flow it is part of, is itself one of the most extraordinary facts about the universe, not a fact that changes the trajectory, not a fact that softens the ending, but a fact. The light we see when we look at the night sky is old. The light from the nearest stars left them years ago. The light from the nearest galaxies left them millions of years ago. The light from the most distant objects we can observe left them billions of years ago, when the universe was young and dense and full of the energy of its recent beginning. We are not seeing the universe as it is. We are seeing the universe as it was, at various moments in its past. The light from each moment arriving at our eyes after a journey, whose length is measured in the age of the universe itself. The night sky is not a window onto the present. It is a window onto the past. A layered, time-delayed portrait of a universe that has been changing, expanding, cooling, and darkening for 13.8 billion years, and that will continue to change, expand, cool, and darken for durations that make 13.8 billion years look like an opening sentence. And the light is fading, not in the sense that the stars are going out tonight, or this century, or this millennium, but on the timescales that the universe operates on, the light is fading. The rate of star formation has been declining for billions of years, since its peak in the early universe when galaxies were young and gas was abundant and the cosmic web was still assembling itself. The universe is past its brightest moment. It has been dimming slowly for most of its history. The stars that exist today are the survivors of a process that was once far more vigorous, far more productive, far more luminous. The universe we inhabit is not the universe at its peak. It is the universe in its long, slow afternoon, moving toward an evening that will last far longer than the day. This is the final image, not a dramatic explosion, not a sudden darkness, not a moment of destruction that could be pointed to and named. Just the long, slow, patient dimming of a universe that has been burning its fuel since the beginning, and that is, on the timescales that matter, running low. The galaxies will continue to shine for billions of years. The red dwarfs will continue to burn for trillions. The white dwarfs will continue to cool for quadrillions. The black holes will continue to evaporate for durations that have no name in any human language. And through all of it, the voids will continue to grow. The expansion will continue to accelerate. The horizon will continue to close. The isolation will continue to deepen. And the silence that already characterizes most of the universe, the silence of the supervoids and the empty spaces between galaxies and the cold dark regions between stars, will continue to spread, slowly and inexorably, until it has claimed everything. Not with fire, not with collapse, not with the dramatic finality of a universe that ends in a moment of catastrophic destruction, but with distance, with separation, with the slow, cold, patient work of dark energy on the fabric of space, pushing everything apart, growing the voids larger, carrying the light beyond the horizon, erasing the evidence, deepening the silence. The universe does not end. It disperses. It does not die. It fades. It does not collapse into nothing. It expands into everything, into an infinite, cold, dark, maximally disordered expanse of space in which the distinction between something and nothing has become, for all practical purposes, a matter of definition. The emptiness was never the background. It was always the destination. The matter, the light, the structure, the complexity, all of it was always moving toward the void. All of it was always, in the language of thermodynamics, a temporary deviation from the universe's preferred state. And the preferred state, the state the universe is always moving toward, the state it will eventually reach, the state it has already reached in the supervoids and the deep empty chambers of the cosmic web, is silence, is darkness, is the cold, patient, infinite expanse of space with nothing in it worth the name of something. We are here, in the brief window. We are the temporary eddies of order, the cosmologically improbable minds, the local exceptions to the universal rule of emptiness. We are the universe looking at itself, for a moment, before the moment passes. We are the light that the void has not yet claimed, and the void is patient. It has all the time in the universe. It has, in fact, more time than the universe has matter, more time than the universe has light, more time than the universe has anything that could be called an event or a process or a change. The void has the rest of forever, and forever, in the end, belongs to the silence. Look up at the night sky one more time. Look at the stars scattered across the darkness, the faint smear of the Milky Way, the soft glow of distant galaxies at the edge of what the eye can detect. It looks full. It looks populated. It looks like a place where things are happening, where the universe is alive and active and rich with presence, and in a narrow, local, temporary sense, it is. But the darkness between the stars is not the background. The darkness is the truth. The stars are the exception. The light is the deviation. The silence is the rule. And the rule, given enough time, always wins. The universe is not mostly what you see when you look up. It is mostly what you cannot see. The dark matter threading the cosmic web, the dark energy filling every cubic meter of space, the vast, empty voids that dominate the volume of the observable universe, the cold, dark future that waits beyond the last red dwarf and the last evaporating black hole and the last decaying proton. The universe is mostly absence, mostly distance, mostly the expanding space between things that are themselves mostly empty, and it is moving, always moving toward more of the same, toward greater absence, greater distance, greater emptiness, greater silence. This is not a comfortable conclusion. It was never going to be. The universe does not owe us comfort. It does not arrange itself for our reassurance or soften its trajectory for our benefit. It is what it is. Vast, mostly empty, accelerating, cooling, darkening, moving toward a final state of maximum entropy, in which the conditions for complexity in life and mind are not just absent, but thermodynamically forbidden. The universe is not ending. It is completing. And completion in this context looks like the void, looks like the silence, looks like the cold, dark, infinite expanse of space that the Bode's void already embodies, that the supervoids already preview, that the accelerating expansion is already building, 1 billion light-years at a time, one evaporating galaxy cluster at a time, one fading star at a time. The emptiness is not the opposite of reality. It is the final form reality is moving toward. It is the destination written into the physics of the universe from the moment of its beginning, written into the low entropy initial condition that set the arrow of time, written into the dark energy that drives the acceleration, written into the second law of thermodynamics that ensures entropy always increases, written into the quantum vacuum that will outlast every star and every galaxy and every black hole and every atom of ordinary matter. The emptiness is not what the universe becomes when it fails. It is what the universe becomes when it succeeds, when it has run every process to completion, exhausted every gradient, dispersed every structure, and arrived at the state toward which it was always moving. And we are here now, in the middle of it, in the brief, extraordinary, cosmologically improbable middle of a story whose ending is already written. We are the universe's temporary exception to its own rule. We are the light before the silence. We are the structure before the void. We are the question the universe asks itself before it forgets how to ask. And the asking, the brief, bright, thermodynamically improbable act of looking into the darkness and wondering what it means, is perhaps the most remarkable thing the universe has ever done with the time it has before the silence claims it, not because it changes anything, not because it delays the ending or softens the trajectory or offers any escape from the void that waits at the end of every arrow of time, but because it happens at all. Because in a universe that is mostly emptiness, mostly darkness, mostly silence, there is, for now, briefly, locally, improbably, a light that knows it is a light, and that knows, with the same clarity with which it knows everything else, that the darkness is coming, that the void is patient, and that the distance in the end is absolute. There is a specific moment that happens to every person who has ever seriously studied cosmology, not the moment of learning the facts, which comes gradually, through years of reading and calculation and observation, but the moment when the facts stop being facts and start being real, when the numbers stop being numbers and start being the actual dimensions of the actual universe you actually live in. It is not a pleasant moment. It does not arrive with fanfare or revelation. It arrives quietly, usually alone, usually at night, usually when the mind has relaxed its defenses enough to let the scale of things through without filtering it into something manageable. And what comes through when the filters drop is not wonder. Not exactly. It is something closer to the feeling of standing at the edge of a very high place and looking down, a feeling that is partly awe and partly the recognition that the ground is very far away and that the distance is not metaphorical. That feeling is the appropriate response to the universe, not the sanitized wonder of a planetarium show, not the comfortable amazement of a nature documentary, not the reassuring narrative of a cosmos that is vast, but somehow arranged for our benefit, or at least our comprehension. The appropriate response is the one that comes when you let the actual numbers through. When you let the 330 million light-years of the Bode's void be 330 million light-years, when you let the 95% of the universe that is dark matter and dark energy be genuinely unknown and genuinely dominant, when you let the accelerating expansion be genuinely accelerating and the heat death be genuinely coming and the silence be genuinely the destination. The appropriate response is the one that does not look away. Most of us look away. It is not a failure of courage. It is a feature of the mind, a mind that evolved to navigate a savanna, to track prey and avoid predators and maintain social bonds and plan for the next season, not to contemplate the thermodynamic fate of the universe on timescales of 10 to the 100th years. The mind is not built for this. It was not designed by evolution or by anything else to hold the actual scale of the cosmos without flinching. The flinching is built in. The looking away is the default. The comfortable reduction of the universe to something human-sized, something navigable, something that fits within the frame of a life. That is not a distortion. That is survival. That is the mind doing what it was built to do. But the universe does not care what the mind was built to do. The universe does not adjust its scale to fit human cognition. It does not slow its expansion to match human timescales. It does not populate its voids with matter because emptiness is uncomfortable. It does not preserve its history beyond the cosmic horizon because knowledge is valuable. It does not arrange its thermodynamic trajectory to avoid the heat death because endings are sad. The universe is not cruel. It is not indifferent in the way a person can choose to be indifferent. It is indifferent in the way that a physical law is indifferent, completely, without exception, without the possibility of appeal. The second law of thermodynamics does not make exceptions for minds that would prefer a different outcome. Dark energy does not pause its work because the expansion is inconvenient. The horizon does not stop closing because there is still so much we want to see. And this is the thing that the voids teach, if you are willing to be taught by them. Not the comfortable lesson that the universe is vast and we are small and we should be humble. That lesson is true, but it is also safe. It is the lesson that leaves you feeling appropriately awed without requiring you to change anything about how you understand your situation. The uncomfortable lesson, the one the voids actually teach, the one that the physics actually implies, is that the universe is not just vast, it is mostly empty. And the emptiness is not the background against which the interesting things happen. The emptiness is the point. The emptiness is what the universe is, at its largest scales and in its final state. The matter, the light, the structure, the complexity, all of it is the exception. All of it is the deviation. All of it is the temporary, local, thermodynamically improbable condition that the universe is always in the process of correcting. The correction is slow. It operates on timescales that make human history invisible. It operates through processes, gravitational dynamics, stellar evolution, cosmic expansion, thermodynamic equilibration, that are so gradual, so patient, so utterly indifferent to the urgency of any individual life or any individual civilization, that they are effectively invisible on any timescale that matters to a human being. The correction is not something you will see in your lifetime. It is not something your civilization will see in its lifetime, if civilizations have lifetimes measured in thousands or even millions of years. But it is happening. It has been happening since the Big Bang. It will continue happening long after the last star has gone cold, and the last black hole has evaporated and the last proton has decayed. The correction is the universe's most fundamental activity. Everything else, every star, every galaxy, every planet, every organism, every thought, is a byproduct of the correction, a temporary elaboration on the journey from low entropy to high entropy, from structure to void, from light to silence. There is a particular kind of knowledge that is harder to carry than ignorance, not because it is painful in the way that personal loss is painful, or frightening in the way that immediate danger is frightening, but because it changes the frame. It changes the context within which everything else is understood. The knowledge of the universe's scale and trajectory and ultimate destination is that kind of knowledge. once you have genuinely absorbed it, once you have let the numbers be real and the implications be real and the destination be real, you cannot unknow it. You cannot return to the frame in which the universe is a backdrop for human drama, in which the stars are decorations on the ceiling of a world arranged for human habitation, in which the darkness between the galaxies is simply the absence of light, rather than the dominant condition of reality. The frame has changed, and the changed frame changes everything that is understood within it. It changes how you understand time. Not the time of a human life, which remains what it always was, brief, precious, irreplaceable, but the time of the universe, which is so vast that the entire history of human civilization occupies a fraction of a fraction of a fraction of it. The universe has been running for 13.8 billion years. Human civilization, in its broadest definition, has existed for perhaps 10,000 years. The ratio between these two numbers is roughly 1 to 1,400,000. If the age of the universe were compressed into a single year, human civilization would occupy the last 2 seconds of December 31st. Everything you have ever known, everything your species has ever done, every war and every discovery and every work of art and every act of love, all of it fits in the last 2 seconds of the universe's year, and the universe's year is not over. It has barely started. The heat death is not in the next year, or the next 1,000 years, or the next trillion years. It is so far in the future that the universe's current age is not even a rounding error in the calculation. It changes how you understand space. Not the space of a room or a city or a continent or even a planet, but the space of the cosmos, the space that the Bode's void occupies, the space that separates galaxy clusters, the space that dark energy is expanding at an accelerating rate in every direction simultaneously, the space that is, by volume, almost entirely empty, the space that contains, in its vast majority, nothing. No matter, no light, no structure of any kind, just the quantum vacuum flickering at scales too small to see and dark energy doing its patient work of pushing everything apart. The space that is, in its true nature, not the container of the universe but the substance of it, not the emptiness between things, but the thing itself, of which matter and light are the rare and temporary exceptions. It changes how you understand existence, not in the sense of making existence feel meaningless. That is the easy, lazy conclusion. The one that mistakes the absence of cosmic significance for the absence of any significance at all, but in the sense of making existence feel contingent, improbable, dependent on a specific set of initial conditions and physical constants and thermodynamic circumstances that could have been otherwise and that will not persist indefinitely. Existence, the existence of stars, of planets, of life, of mind, is not the default condition of the universe. It is the exception. It is what happens when the universe is far from equilibrium, when the thermodynamic gradients are steep enough to drive complex processes, when the conditions are right for matter to organize itself into structures that do things. Those conditions are not permanent. They are not guaranteed. They are the product of a specific moment in the universe's history, a moment that has been going on for billions of years and will continue for billions more, but that is, on the timescales of the universe's full duration, a brief, an improbable interlude, and it changes how you understand the night sky. Not the night sky as a beautiful spectacle, which it remains. The beauty is real, the light is real, the stars are real, but the night sky as a representation of the universe's true condition, because the night sky as seen from Earth is a profoundly misleading portrait of the cosmos. It shows you the exceptions. It shows you the matter, the light, the structure, the thin, luminous threads of the cosmic web, the burning stars, the glowing galaxies. It does not show you the voids, which are invisible by definition. It does not show you the dark matter, which does not emit light. It does not show you the dark energy, which has no visible manifestation. It does not show you the cosmic horizon, which is not a visible boundary. It does not show you the heat death, which is a future state. The night sky shows you the 4.9%. It hides the 95.1%. It shows you the exception and conceals the rule. The rule is the void. The rule is the darkness. The rule is the cold, expanding, accelerating emptiness that dominates the volume of the universe and that will, in the end, dominate everything. The night sky is beautiful precisely because it is exceptional, because the light it shows you is rare, temporary, and surrounded on all sides by a darkness that is far more fundamental than the light. The stars are beautiful the way a fire is beautiful in a very large, very cold, very dark room, not because the room is warm, because the fire is the only warmth there is, and the room is enormous and the fire will not burn forever. There is a question that children ask sometimes when they first learn that the universe is expanding, when they first learn that the galaxies are moving apart, that the space between them is growing, that the universe is getting larger with every passing second. The question is, what is it expanding into? What is outside the universe into which the universe is growing? It is a natural question. It is the question that the intuition demands, because every expansion we have ever experienced, every balloon inflated, every city grown, every empire extended, has been an expansion into something, into space that was already there, waiting to be occupied. The intuition insists that the universe must be expanding into something, that there must be an outside. The answer that cosmology gives is unsatisfying in the way that true answers to deep questions often are. The universe is not expanding into anything. There is no outside. The expansion of the universe is not the expansion of matter through a pre-existing space. It is the expansion of space itself, the growth of the metric, the increase in the distance between points, the stretching of the fabric of space-time. There is no edge to the universe beyond which empty space waits to be filled. There is no container. There is no outside. The universe is not a thing in space. It is space, along with everything in it. And the space is growing, and there is nothing outside it for it to grow into, because outside it there is not even nothing. There is not even the absence of something. There is simply the inapplicability of the concept. This is one of the places where human intuition fails completely and irrecoverably. The mind cannot genuinely hold a universe with no outside. It can say the words. It can follow the mathematics. It can accept the conclusion intellectually, but it cannot picture it. It cannot feel it. The intuition keeps reaching for the outside, keeps asking what the universe is expanding into, keeps insisting that there must be something beyond the boundary, and the answer keeps being the same. There is no boundary. There is no beyond. The universe is all there is, and all there is expanding, and the expansion has no destination because there is nowhere for it to go except into more of itself, and the voids are part of this. The voids are not holes in the universe. They are not regions where the universe is absent. They are regions where the universe is present in its most fundamental form, as space expanding, cold, dark, and empty of the matter that temporarily populates other regions. The voids are not the universe's failures. They are the universe's substance. They are what the universe is made of, at the level where matter is the exception and space is the rule. They are the universe being itself, without the temporary elaboration of structure and light that makes it recognizable to the minds it briefly produces. Follow this to its end. Follow it past the heat death, past the evaporation of the last black hole, past the decay of the last proton, past the Boltzmann brains and the quantum fluctuations and the cold, dark silence of maximum entropy. Follow it to the question that waits at the very end of the trajectory, the question that the physics raises and cannot answer, the question that sits beyond the boundary of what science can address, and that every mind capable of following the argument to its conclusion must eventually face alone. The question is not what happens after the heat death. The question is why there was anything before it, why the universe began in a state of extraordinarily low entropy, why there was a Big Bang at all, why there is something rather than nothing. This is the oldest question in philosophy. It predates cosmology by millennia. It has been asked in every culture, in every language, in every era of human history, and it has never been answered. Not because the question is unanswerable in principle. Perhaps it is answerable. Perhaps a future theory of quantum gravity or a future understanding of the multiverse will provide something that functions as an answer. But because no answer currently exists that is both scientifically grounded and genuinely satisfying, the universe exists. It began in a specific state. It is evolving according to specific laws, and we do not know why. We do not know why there is a universe rather than nothing. We do not know why the laws of physics are what they are rather than something else. We do not know why the initial conditions were what they were rather than something else. We do not know, in the deepest sense, what the universe is or why it is here. And this ignorance is not a temporary condition that will be resolved by the next generation of telescopes or the next breakthrough in theoretical physics. It may be a permanent condition, a feature of the relationship between minds and the universe they inhabit, a consequence of the fact that minds are part of the universe and cannot step outside it to examine it from a neutral vantage point. The universe cannot explain itself to itself. The part cannot fully comprehend the whole. The temporary eddy of order cannot fully understand the flow it is part of. The light cannot see the darkness that surrounds it, because seeing requires light, and the darkness is defined by its absence. We are the universe's attempt to understand itself. That is not a metaphor. That is a literal description of what is happening when a mind studies cosmology. When a human being uses instruments built from matter to observe matter, uses mathematics developed by minds to describe the behavior of the physical world, uses the laws of physics discovered through experiment to predict the fate of the universe that produced the experimenters. The universe is, through us, examining itself, measuring its own expansion, mapping its own structure, calculating its own fate, and finding at the end of the calculation that the fate is silence, that the universe it is examining is moving toward a state in which the examination is no longer possible, in which the conditions for minds and instruments and mathematics and questions have been thermodynamically exhausted. The universe is examining itself and discovering that it is running out of time to do so, not on any human timescale, not on any timescale that should cause immediate concern, but on the timescales that the universe itself operates on. The window of self-examination is finite. The conditions that make minds possible, the burning stars, the stable planets, the chemical complexity, the thermodynamic gradients, are temporary. They will not persist. And when they are gone, the universe will continue, but it will continue without the capacity for self-examination. It will continue as a cold, dark, maximally disordered expanse of expanding space, with no part of it capable of asking what it is, or why it exists, or where it is going. The question will have been extinguished along with the questioners, and the universe will not notice. It will not mourn the loss. It will simply continue as it always has, according to its laws, toward its destination, indifferent to the silence it is creating. This is the final, unsettling fact. Not that the universe is large or mostly empty, or accelerating toward heat death. Those are unsettling, but they are unsettling in a way that can be held at a distance, examined as features of a cosmos that is separate from the examiner. The final unsettling fact is that the examiner is not separate. The mind that finds the universe unsettling is part of the universe. The discomfort is the universe's discomfort with itself. The universe, through the temporary structure of a mind, registering the implications of its own trajectory and finding them difficult to hold. The vertigo is not a human response to an inhuman universe. It is the universe's own response to what it is, expressed through the only medium capable of response. The brief, improbable, thermodynamically doomed structures of matter and energy that it temporarily organizes into minds. And the minds will not last. They are already on cosmic timescales almost gone. The window during which the universe produces minds, during which the conditions are right for the emergence of self-awareness and self-examination, is narrow. It requires burning stars for energy, stable planets for chemistry, billions of years for evolution, and a specific range of thermodynamic conditions that will not persist indefinitely. The universe has been producing minds, as far as we know, for only a small fraction of its current age. It will continue to produce them perhaps for billions of years more. But billions of years, in the context of the universe's full duration, is nothing. It is less than nothing. It is a rounding error in a calculation whose answer is measured in exponents of exponents. The minds are a brief feature of the universe's middle period, a temporary elaboration that arises when the conditions are right and dissolves when they are not. And the conditions are not permanent. The stars are burning down. The gas that feeds star formation is being consumed. The thermodynamic gradients that drive the complexity required for life and mind are being smoothed out slowly, by the same entropy that is smoothing out everything else. The universe is not moving toward more minds. It is moving toward fewer. It is moving toward none. And after none, it will continue moving, as it always has, toward the silence that was always its destination. Look at the boat as void one final time, not with the eye, which cannot see it. It is too large, too empty, too far away for any human sense to register. Look at it with the mind, which is the only instrument capable of holding it, 330 million light-years across, a sphere of near-nothingness embedded in the cosmic web, surrounded by the thin luminous threads of galaxies that define its boundary, growing slowly as dark energy does its work, as the matter at its edges drains toward the surrounding filaments, as the space inside it expands and the temperature inside it drops and the silence inside it deepens. It has been there for billions of years. It will be there for billions more. It will outlast every star currently burning in the galaxies that surround it. It will outlast the galaxies themselves. It will outlast the black holes at the centers of those galaxies. It will outlast, in a sense, everything, because the void is not a thing that can be exhausted or consumed or evaporated. It is the absence of things, and the absence of things is the one condition that the universe's thermodynamic trajectory guarantees will increase not decrease, with time. The void is patient. It does not need to do anything. It does not need to expand aggressively or consume matter or overcome resistance. It simply waits, and the universe comes to it. The matter drains away, the stars burn out, the galaxies fade, the black holes evaporate, the protons decay. And with each of these processes, the universe becomes a little more like the void, a little emptier, a little colder, a little darker, a little closer to the condition that the Buddha's void already embodies. The void is not the universe's enemy. It is the universe's future. It is what the universe is becoming, one star at a time, one galaxy at a time, 1 billion years at a time. And we are here now, in the part of the universe that is not yet void, in the part that still burns, still glows, still organizes itself into structures complex enough to ask questions. We are in the exception. We are in the deviation. We are in the brief, bright, thermodynamically improbable region of the universe that has not yet been claimed by the silence. And the silence is not rushing. It does not need to rush. It has all the time that exists, and all the time that exists is, in the end, on its side. There is nothing to be done about this. That is not a counsel of despair. It is a statement of fact. The thermodynamic trajectory of the universe is not a problem to be solved. It is not a challenge to be overcome. It is not a condition that can be reversed or delayed by any action available to any mind or any civilization operating within the known laws of physics. The entropy will increase. The expansion will accelerate. The horizon will close. The stars will fade. The voids will grow. The silence will deepen. These are not predictions that depend on human choices or human failures. They are consequences of the laws of physics applied to the initial conditions of the universe, and they will unfold regardless of what any mind or any civilization does or fails to do. What can be done, what is being done right now in this moment by every mind that looks up at the night sky and asks what it sees, is the asking, the examination. The brief, improbable, cosmologically insignificant, but locally extraordinary act of a temporary structure of matter, using the laws of physics to understand the universe that produced it. This is not nothing. It is not everything. It does not change the destination. It does not soften the ending. But it is what is available in the window that remains to the minds that the universe has temporarily produced. And it is, in its own way, the most remarkable thing that has ever happened in the 330 million light years of the Buddha's void's cold, dark, patient interior. Not because it matters to the void. The void does not register it. The void does not care. But because it happens at all. Because in a universe that is mostly emptiness, mostly darkness, mostly silence, there is, for now, a light that knows what it is looking at. The light knows it is looking at its own ending. It knows the void is growing. It knows the silence is coming. It knows that the distance in the end is absolute, that the expansion will carry everything beyond the horizon, that the entropy will smooth out every gradient, that the heat death will claim every structure, that the universe will complete its journey from the extraordinarily ordered beginning to the maximally disordered end, and that the completion will look, from the inside, like the permanent extinguishing of everything that could be called an event. The light knows all of this, and it looks anyway. It asks anyway. It maps the cosmic web and measures the expansion and calculates the evaporation time of black holes and contemplates the heat death and sits with the discomfort of what the physics implies, and it does not look away. That is the only answer the universe offers to the question of what it means to exist within it. Not comfort, not reassurance, not the promise of permanence or the guarantee of significance, just the looking, just the asking, just the brief, clear-eyed, unflinching examination of a universe that is mostly void, mostly dark, mostly silent, and moving, always moving, patiently and without exception, toward more of the same. The universe does not explain why it is here. It does not justify its structure or apologize for its destination. It simply is what it is, and what it is, at its largest scales and in its final state, is the void. The void was here before the stars. It will be here after them. It surrounds every galaxy, fills every supervoid, underlies every structure, and waits with the patience of something that does not experience waiting, for the matter and the light and the complexity and the minds to finish their brief elaboration and return to the silence from which, in a sense, they never fully departed. The universe began in a state close to void, hot and dense, yes, but uniform, featureless, without the structure that would later emerge. And it will end in a state close to void, cold and sparse and maximally disordered, without the structure that briefly arose in the middle. The void is the beginning, and the void is the end, and the void is the dominant condition of everything in between. We are in the middle. We are the middle. We are the brief, bright, structured, questioning middle of a story, whose first and last chapters are both written in the language of emptiness, and the middle is ending. Not today, not this century, not this geological era, but on the timescales that the universe operates on, the middle is already ending, has been ending since the peak of star formation billions of years ago, is ending now as the expansion accelerates and the horizon closes and the evidence is carried away, will continue ending as the last stars cool and the last black holes evaporate and the last structures dissolve into the featureless background of maximum entropy. The middle is ending. The void is waiting. The silence is the destination, and the only thing left to say, the only thing that the physics, followed honestly to its conclusion, leaves room for, is this: we were here, in the brief window, in the exception, in the light before the silence. We looked at the void and we understood, at least approximately, at least partially, at least for the moment that we had, what we were looking at. We did not look away, and the void, patient and absolute and indifferent as it is, did not need us to. It was always going to be there when we were done. It is always going to be there. It has all the time that exists, and all the time that exists, in the end, is silence.